I welcome all the directors of the consulting institutions and off-campus center, deans, academics, student affairs, nodal officers of HBNI, conveners, board of studies from all the CAs for the one-day seminar, the joint group online. I welcome all our doctoral students and postgraduate and graduate students who have joined us online for the seminar on India's tech engines for Viksit Bharat breakthrough in semiconductor research. On behalf of HBNI, I especially welcome all our speakers, Dr. Shashwat Singh Eram, Dr. Sulabh Gupta, Dr. Mukesh Ranjan, Dr. Tarun Kumar Sharma, Dr. Kishore Kumar Madhupur, for accepting our invitation in the last minute and ready to deliver lectures. I especially welcome all our speakers for this seminar. I once again submit my thanks to all the speakers and welcome you all to the seminar. With this, may I request our Honorable Vice Chancellor, Professor Kamachi Mudali, for presenting his introductory remarks. Sir.
Very good morning. I welcome all of you for the seminar on India's decade chips for Viksit Bharat, breakthrough in semiconductor research. All of you must be wondering that it is very quickly called seminar. We received intimation on Monday evening that all the new universities should do live streaming and also conduct a program on the occasion of laying foundation stone for 3 semiconductor units by our Honorable Prime Minister Narendra Modi. So yesterday we have received a call and we had an interaction session with the UGC secretary, and we deliberated about how to conduct this program and what we should do for live streaming of the foundation stone laying ceremony for 3 of the units that will be held today. So, in this quick notice, I would like to first appreciate all the speakers who have agreed to our notice and prepared lectures on subject breakthroughs that is related to semiconductor research from various units. I'm very happy that the lecture on germanium semiconductor material for Viksit Bharat will be delivered by Dr. Saptati Sen Eram from DRC, and she will talk on the germanium semiconductor material for Viksit Bharat. And lecture 2 will be on high purity silicon for semiconductor and radiation detector industry. That will be delivered by Sri Sulabh Gupta from DRC. And we have the lecture 3, semiconductor processing using plasma and ion beam by Dr. Mukesh Ranjan from Institute for Plasma Research, Gandhinagar. And the next lecture 4 on fabrication of compound semiconductor chips for lasers and detectors by Dr. Tarun Kumar Sharma from Rajaramana Center for Advanced Technology, Indore. And the last lecture will be on the monolayer MOS2 molybdenum disulfide for flexible and high mobility electronics by Dr. Kishore Kumar Madhupur. He is from Indira Gandhi Center for Atomic Research, Kalpaka. And Dr. Datta, Dipanwita Datta, who is our associate dean, has coordinated and organized all these lectures for this seminar. And in between 10:30 to 11:30, we also do the live streaming of the foundation stone laying ceremony for 3 semiconductor facilities in India by the Honorable Prime Minister of India, Sri Narendra Modi ji. I would like to also give you some brief information that recently the Indian Cabinet has approved the establishment of 3 semiconductor units under the development of semiconductors and display manufacturing ecosystems in India. These 3 units will be constructed within next 100 days. That was the decision also by the Indian Cabinet. And this program for development of semiconductor and display manufacturing ecosystem was notified in 2021 with an outlay of 76,000 crore. And in 2023, the Cabinet also approved the proposal of Micron, international giant in semiconductor industry from USA, to set up a semiconductor unit in Sanand, Gujarat. So this unit is going on very well in a rapid pace, and the emerging of the semiconductor ecosystem is going to be sooner once this unit is also coming into action. The three semiconductor units that will be today inaugurated by, or I will say, the laying foundation stone will be done by the Honorable Prime Minister. Or one is the semiconductor fab with 50,000 wafer starts per month. That is jointly by the Tata Electronics Limited with our chip semiconductor manufacturing of Taiwan. And this is at Golera, Gujarat, at the cost of 91,000 crore. And the technology partner, the PowerSic Semiconductor Manufacturing Corporation, is a very renowned, expert in logical memory foundry segment. And they have 6 semiconductor foundries in Taiwan, and so this is a very strong partnership to develop 50,000 wafer starts per month. The second one is the semiconductor ATMP unit, that is the unit for the packaging. This is also partnered with Tata Semiconductor Assembly and Test Private Limited, that is TSAT. They will set up at Morigaon in Assam, and there is with an investment of 27,000 crores. And this technology that will be used is the TSAT Semiconductor is developing indigenous advanced semiconductor packaging technology, which includes flip chip and integrated system in packaging technology. The capacity will be 48 million per day, and they are covering the packaging for integrated system in packaging for automotive, electric vehicle, consumer electronics, telecom, mobile phones, etc. The third unit is the semiconductor ATMP unit for specialized chips, and that is done by CG Power in partnership with Renesas Electronics Corporation Japan and the Stars Microelectronics Thailand. And they will also set up this unit, Sanand, where Micron is setting up another unit from 2023. And this investment for this plant will be 7,600 crore. And Renesas is a leading semiconductor company focused on specialized chips. They operate a 12 semiconductor facility and an important player in microcontrollers, analog, power, and system-on-chip products. And they cover the segment of consumer, industrial, automotive, and power applications. The capacity is 15 million per day. And these three units will also generate direct employment of 20,000 advanced technology jobs and about 60,000 indirect jobs. And these three units will accelerate employment criterion in downstream automotive, electronics manufacturing, telecom manufacturing, industrial manufacturing, and other semiconductor consuming industries. This is very, very important today because, as you all know, that according to the data available, the Indian semiconductor market is currently $34.3 billion in 2023, and this is projected to be around 100 billion by 2032, with an annual growth rate of compound annual growth rate of 20%. So that is the speed in which the growth is going to happen in the Indian semiconductor market from 2023 to 2032 in this 10 years. So before Viksit Bharat, many things will be happening in our country, so that by Viksit Bharat we will become a technology period in semiconductor field. And this is very, very important. As you all know, I have mentioned also during setting about the pre-planned information that electric vehicles is going to come in a big way. That is one sector that I am telling where semiconductor use is going to be required. There are other aspects like safety, electrification, communication, and networking. All of them are increasing, and there are a lot of requirements for chips that will be designed specifically for various applications in which will definitely transform the semiconductor industry in our country today. So I'm very happy that on this occasion of laying foundation ceremony for all these three plants in our country, one in Gujarat, one in Assam. So we are organizing this seminar as per the direction by the UGC, University Grants Commission, And also that we will be live streaming immediately the seminar, the function where the laying foundation stone will be done by the Honorable Prime Minister and also addressed by the Honorable Prime Minister this occasion. I welcome all of you and I am sure that the lectures will be very useful and they are all very highly focused and specific lecture on semiconductor research. By attending all these kind of lectures, I am sure that all of you will get state of the art knowledge on what we are doing in our department as well as in our country. Thank you very much.
Thank you, sir, for your excellent briefing about the program. Now, so we go to the lectures. It's now the first lecture. The first lecture is going to be delivered by Dr. Shashwati Sen. Dr. Shashwati Sen is currently getting the Crystal Technology section of Technical Physics Division of BRS and working on the growth of scintillator and semiconductor single crystals for the application of radiation detection. Dr. Shashwati Sen has special interest in developing devices using single crystals for several applications. Dr. Shashwati is the recipient of the DAE Science and Technology Excellence Award 2017, DAE SSPS in Achievers Award YAA 2008, and DAE Group Achievement Award in 2008 for the work on gas sensors, and in 2014 for the growth of single crystals of cesium iodide and sodium iodide for radiation detection. She has more than 200 publications in international peer-reviewed journals and has been instrumental in technology transfer to local industries on the growth of cesium iodide single crystal for radiation detection as well as for the growth of oxide single crystals. May now request Dr. Shashwati Sen to deliver the presentation. Thank you, ma'am, for accepting our invitation in the short notice. Please proceed, ma'am.
Good morning, everyone. Thank you for my introduction. And first, I will like to start with thanking Honorable Vice Chancellor HBNI for giving me this opportunity to talk to this wide audience and on this very auspicious occasion where we are like laying the stepping stone towards a Viksit Bharat with very integrated program on semiconductors. So what I'm going to talk today is germanium semiconductor material for Viksit Bharat. First, let us start from where the semiconductor story of the semiconductor started. So this started with the birth of transistor in 1947 on 24th December. So this started with the discovery of transistor by the three scientists, Bardeen, Shockley, and Brittain at the Bell Laboratories, where they used this double point contact was made. This is a germanium substrate crystal they have used, and they have made this two contacts, top and bottom, and they have shown the transistor properties. So here you can see the date is there, and this is from their logbook. So this started the journey of semiconductor, and from 1947 to today, 2024, we know that semiconductors is ruling our life. So semiconductor, when we are talking about the two intrinsic semiconductors, we all know. So they are like, first one is the silicon, which is prevalent everywhere. So silicon, as we see, is in the 14th number, and it is a hard brittle crystalline solid with blue gray metallic structure, and it is abundant in nature. Nature has given it its present in the earth crust around 25% by mass and just after oxygen, and from sand we know it is all silicon. So, and the other brother, I would say, of the semiconductor industry of silicon is the germanium. But unlike the silicon, germanium is very rare. So we can see that this is present as a trace material in the earth's crust with an average concentration of 1.6 ppm, parts per million. And it was first isolated in 1886 from the mineral. So, but these both are playing very important role. And my focus of the talk will be more on germanium. But before that, I will just give a very glimpse of why it is important, why our government is working on promoting the semiconductors. So if we see this graph, so on the x-axis, we have like the relative economic importance. So as we go on the x-axis, it is the economic importance. And if we go on the y-axis, it is the supply risk. So Government of India, Niti Aayog has placed all the materials, important materials in this 4 zones, and where the zone 1 is like high economic importance and high supply risk. And here we see we have got both silicon and germanium. So the source of germanium is like 100 milligram per kg we have seen, and it is found in the zinc ore. It is not also present as a independent germanium, and also in coal fly ash. So it is important to initiate necessary action from today itself so that we can secure the sources of both silicon and germanium in the country. Now coming to the silicon, we can see both silicon and germanium. So these are the silicon crystals and this is the germanium. So if we see application of single crystal, both this material are used in the form of single crystals when we are talking about chips or we are talking about ICs. So they are basically silicon or germanium wafers. So if we see the application of single crystals, 60% of the market share is covered by the semiconductors, these 2 materials. Though these 2 materials are both intrinsic semiconductors, but they have got their own properties. We can see that in the terms of band gap, silicon is 1.1, whereas germanium is 0.6. The energy required to produce 1 electron hole pair for germanium is like 2.9, whereas for silicon is 3.7. The electron and hole mobility of both for germanium is higher than silicon. So in specific applications, like where we want very high output or very high efficiency, we go for germanium. But rest all, because of the abundance in nature, silicon is more used. Now coming to the silicon market. So as our Honorable Vice Chancellor has already said that the global silicon market as of today is like 6.3 billion in 2019, and it is going to be around 8.9 US dollar billion in 2027, and with a compound annual growth rate of 5.5. And if we see the major countries where silicon production is happening, so the major chunk is like China, and here we have got India, which is producing around 59,000 metric tons per year. But for taking this into view, our Indian government has started in December 21, a $10 billion incentive plan has started. And in this, you can see that in the business line, we can see that India lacks talent for chip manufacturing and requires resources. And then, but in this line, it has started from long back, like the first Indian producer of large monocrystalline silicon ingot. It has been started in December 2022 by Adani Solar. And today is just one stepping stone where stone for 3 such wafer producing and fab labs from silicon. Now coming to the germanium, we see that in the world market, we see that the germanium based semiconductor market in 2020 was around 17 billion US dollar, and it is expected to go to 26 billion US dollar. Now again, 80% of world production is from China. You can see here, this is China. So from 2009 to 2018, I am saying. And then other countries are there, very small, and something from Russia. Now the use of germanium is very high technology importance are there, like infrared. Yeah. So coming back now, this high technology applications where germanium plays a part of the infrared system, fiber optics, polymer catalysis, solar cells, and all. I will show you better here. So, single crystals for IR optics. So, IR optics, like germanium, has got a transmission range of 2 to 13 micrometers wavelength. So, these are used in the night vision strategic cameras. Similarly, because of very high mobility, which I have shown for electrons and holes, it is used in high-speed semiconductor devices like the germanium N MOSFET is there. Similarly, is used for high efficiency substrates for LED, silicon, germanium microchips, and photovoltaic application mainly. This is used in solar cells. In the space application, where the solar photons are very less and very high efficient solar cells are required. And then coming to the high resolution gamma spectrometer, these are used for the high pure germanium crystals. So here are the worldwide end use of germanium. So here I have shown that similar infrared optics. We have using germanium and germanium oxide as glasses and camera lens. And then electronics, silicon and germanium base chips for high speed. And then semiconductor, we have got N-type germanium, and it has doped with different dopants. Then diodes are there, transistor, and solar cell, and radiation detectors. So here we can see like 30% is of germanium is used in the infrared optics, 25% in fiber optic system, then 25% in some polymerization catalyst, solar cell application, and a very small 5% is on the chemotherapy, radiation, and radiation detector. So here my talk today is on this radiation detector because it is very important to DAE, and today I will be talking on the DAE's contribution on the high purity germanium radiation detectors. So what is basically a high purity germanium radiation detector? So it is like a gold standard for gamma spectroscopy. So if we see, this is a typical gamma spectrum. So this blue spectra which we see is what we can get from a HPG, high purity germanium detector, whereas this red line we see, which we can detect using a normal scintillator like sodium iodide, which is conventionally used. So typical energy resolution is 1.5 keV at 662 keV against 40 to 45 keV for a sodium iodide scintillator detector. So because of this very small full width at half maximum for the germanium detector, it has got very high energy resolution. So that's why when there are a lot of unknown radioisotopes are there, or some like in units like IGCAR, where we have got power reactors, accelerator, plutonium plant. So HPG is like bread and butter to know the kind of radioisotopes we are using. Even in high energy physics accelerators or high energy physics experiments, HPG is required. And similarly, nowadays in healthcare, where we are using radioisotopes for diagnostics as well as for detection as well as for curing tumors and cancer therapy, HPG is being used more and more. Now, coming to the Indian scenario, there is not a single company who is making the HPG detector. I would like to emphasize here that in full over the world, there are only two companies. One is Canberra and one is Vortec. Both, one is in US, another is in Europe. Who are making this HPG detector. Because as we come to the later slides, we can see that technology is very difficult, and that's why only two companies are working on it. And a typical HPG detector costs around 20 to 50 lakhs, depending on the size of the crystal and application. And also, its supply to DAE unit is very restricted because of its strategic nature. So, at the heart of this detector is the A13N pure germanium crystal. So, that is why it is called high pure germanium crystal. Now comes, what is this 13N? What do I mean by this 13N? So when we say that 24 karat gold, let's talk about the 24 karat gold, which has got 99.99% purity. But a 13N germanium purity, when I say it is like 99. We have got 11 nines. So that is like 9 purer than our 24 karat gold. So if we talk in terms of number of atoms, so number of atoms per cubic centimeter volume of germanium is 4.2 into 10 to the power 22. So for 13 impurity, number of electrically active impurities in 1 cc of germanium is like 4.2 into 10 to the power 9 per cc. So impurity concentration of around 10 to the power 10 impurities are there in 1 cubic centimeter of germanium. That is the kind of purity is required to make a HPG detector. Now, the physics behind the detector is that this belongs to this high intensity signal permits detection and counting of individual radiation events. So how it is happening is basically we have got it is a detector is the HPG. And on that, we make a p-type contact and a n-type contact. So p-type contact is generally made by boron, and the n-type contact is made by lithium diffusion. And very thin contacts are made on the two ends, and in between we are getting the depletion depth. So here, when the radiation comes and deposits its energy in the depletion depth, and this whole diode is maintained in a reverse bias mode. So the electron and hole are formed, and which are generation of charge carrier happens, and this charge carrier is now detected using the electronics, and that is how we can find out the amount of energy, radiation energy, which has been absorbed. Now, the reason for very high purity material we are using is because of this depletion depth. Here we are maintaining a reverse bias of around 1 kilovolt to 2 kilovolt depending on the size of the germanium crystal. So if we see here the depletion depth and the impurity concentration, if we see, so if our bias voltage is say 1 kilovolt and our impurity is like 10 to the power 12 instead of 10 to the power 10, then the depletion depth at 1 kilovolt I will get around only 1 to 2 MeV. But we know that for detection of a gamma energy of say 1 MeV, we require some volume because we have to stop the gamma ray. So this kind of impurity concentration or this kind of 11 impurity will not work. So what we require is like 10 to the power 10, that is the 13 impurity, so that our depletion depth is around more than 10 mm or so. So that is the reason why this kind of impurity levels or this kind of purity, 13 impurity which we use is required. Now, what is the process flow of HPG technology? And this technology DA is working on, and we have been, there is a group in our technical physics division who is working on this full flow chart. So initially we start with commercial germanium, then germanium refinement is done in VRC. Because commercially available germanium, whatever we get is just 6 impurity. So it has to be refined to the 13 impurity level. Then it has to be checked, and then crystal growth is there because wherever the application is there, it has to be in crystal growth. And then surface preparation, Q and QC of crystal growth, and then the detector fabrication. So starting with the purification of the commercially available 6 impurity is done by this zone refinement technique. So basically this zone refinement this is the germanium rod, and we have got a heater. So this is a traveling heater. So what happens, I can show it in the schematic. So this traveling heater is creating a molten zone, and this molten zone is being it is traveled from one end to the other end. Now, in all the semiconductors or all the solids, it has got the property that the impurities which are within the material, it has got different solubility limits in the liquid phase and in the solid phase. So when this molten zone travels from say left to right, so the impurities get segregated and they are left behind in the solid part. Whereas the liquid zone which is moving forward is the higher purity material. So this is carried out again and again, and then we get a high purity material. So this is basically the setup where we are using an induction heater. Here we are keeping the germanium, and these are the bars which are purified. Now the second step comes in after the purification is the single crystal growth. The single crystal growth is carried out by the Czechoslovakian crystal puller technique. This is a Czechoslovakian puller. And here the germanium, high purity germanium material is melted inside a graphite susceptor and a quartz crucible and in hydrogen atmosphere. Because of the very high purity requirement and there should not be any oxygen and other requirements, the full growth is taken care in a 100% hydrogen atmosphere. So in this system, we are using like 300 liters of high pure hydrogen, which is generated by a gas generator. Then the susceptors and the quartz. So we have to remove all the impurities coming from the graphite susceptor and crucible. And there are a lot of other challenges also. And this is how the crystal comes up after the growth. So I will just show you this very small growth movie so that you know how it is happening. So these are the germanium chunks which you can see, and they are heated and it is melted. So this part you can see is the molten germanium, and this is the solid germanium. Now this we can see is the full molten, and in the Zikowski-Puller technique we have a seed crystal. So this is basically a germanium seed crystal which come and touches the molten germanium, and now the seed crystal is being rotated, you can see, and it is also translated upward, and this crystal growth is taking place at this juncture, at the solid and liquid interface. You can see this is growing, okay, and you can see this is the crystal coming up. The crystal is rotating and we are also pulling up. So this is called a puller technique also. This is the germanium molten and this is the crystal grown, and this way the full crystal comes up. So this is the crystal. So this is the Caesar technique for the growth of germanium crystal. Now once the crystal is grown, we have to check it for its purity, its crystallinity. So this crystal is cut and polished. So because we have to make the wafers. And then this is the XRD, Rocking curve, and all those things have to be done. Then now coming to the detector fabrication. So this is basically the HPG single crystal we have grown using the Zikowski technique. And from this, we have to make the single crystal to the diode fabrication, because as we saw that the HPG is basically a PIN diode. So here I am showing this is a quasi-planar structure geometry, in which we have deposited in our lab by thermal deposition and diffusion technique lithium. So lithium is evaporated and then the crystal is heated. So this lithium is evaporated on this full or on all the sides, on the top side, and also on the back of the crystal. Means if this is the crystal, this is like 2 inch by 2 inch. We cut it into half, then we make these grooves, and then this part is all lithium. This side is all lithium, and even this face is lithium. And then for the p-type contact on the very small portion in between, we are implanting boron. So boron is deposition of a boron is by ion implanter, where like boron is evaporated and then it is accelerated to 25 kilovolts, and then it falls on this germanium, and here it makes this p-type contact. So the thickness of the lithium here is like around 500 micron, and the boron is around 300 micron. And rest of the part, the rest of volume is the high purity germanium, which is our depletion region. But as we know that in case of any semiconductors, there is a surface. So we have to passivate the surface so that there is no leakage current which is coming out from the from this unprotected germanium. So this passivation is carried out by various techniques. There is chemical etching. There are a lot of recipes are there. Then we have to physically passivate it, and then the detector is ready. Now, for detection of germanium radiation using a germanium crystal, we have to cool it. Why we have to cool it? Like here in the first slide, I have shown that the energy gap of germanium is like 0.66 eV. So if we are operating the crystal at the detector at room temperature, we will be having lot of already carriers will be there because of the electron hole pairs. And then if electron hole pair is formed because of the incoming radiation, because of the background noise, we will not be able to detect it. So that's why it is cooled to liquid nitrogen temperature. So this is the liquid nitrogen devar, And we have a dipstick cryostat. That is what is called. It is made up of, it's a very sophisticated way of doing it. So we have got a basically copper bar which goes and it touches the liquid nitrogen. And the electronics is also fitted here. So we have got FETs, PT100 and all. And above this, in this portion, the crystal will come and sit. And then this whole assembly is now vacuum envelope is there, because there should not be any condensation. And as I told that this detector is working in 1 kV or 2 kV voltage. So sweating and all those things should not happen. So this is like the feed throughs of 1 kV, 2 kV. This is the vacuum envelope. The crystal is sitting here and the electronics is there, and the whole thing goes into the liquid nitrogen vapor. And the detector holder is like this. The crystal we have seen in the earlier slide, it comes and goes inside this. You can see this is how the full schematic is. This is our crystal which we have made from the germanium after lithium and boron deposition. This is the holder which is there. Now this holder comes here. So this is, then our electronics is there. This will be fully vacuum evacuated. And this is our dipstick cryostat which is going and sitting inside this electrodeva. So that is how a HPG works. And but that is not the end. Now we have to detect the signal, and the signal is like the kind of signal we are getting here is in nanoampere. So we require very high, very less noise and very high efficiency electronics, which all has been made in BRC in-house. This cryostat is also made in BRC by different groups, and electronic group is working on the MCA and the pre-amplifiers, low noise and high efficiency amplifiers. And now finally, this is a working detector. This is fully indigenous, made in BRC, made in DAE. This is in here, this is where the HPG crystal is there. This is the cold junction, this is electronics, and this is going, and this is an elbow kind of cryostat. This going and sitting inside, and here we are applying the high voltage bias, and you can see the signal. And in terms of pulse height spectra, we can see this is 662 keV, which is coming from cesium 137, and cobalt 60 peaks are there. And the full width at half maximum is like 2.6 keV at 662, which amounts to a resolution of 0.39%. So this is a totally indigenous working, and this is import substitute for requirement of DAE as well as other industries also. But it is also like a technology development, so that tomorrow we have this technology in India, and later on we have enough with the local expertise. This can be maybe exported. So if we see the kind of cost effectiveness, so the crystal we are now at present we are buying high purity crystals like 6 lakhs from outside, and then the detector fabrication, cold finger electronics. So this is in the international, it is coming around 40 lakhs, whereas when we are doing it in house, it is maybe coming around 20 lakhs. So around 50% of the foreign exchange we can save, and also this is like a step towards Atmanirbhar Bharat and Viksit Bharat. But this is just the beginning. This is not the end, because ultimately we have to have a full cycle to sustain any such kind of activity. So it starts from recycling of germanium, because the germanium in nature is very less. So whatever is there germanium lying outside or from the old detectors and extraction from germanium from indigenous source, we have to start from there. And this is like next 10 years we will be working on. Then it will be purification of germanium, zone refinement, high purity polycrystalline germanium. From there, the crystal growth, and then after crystal growth, indigenous development of HPG detector with various active volumes. As of now, we have reached to active volume of 50 cc, whatever crystal you are seeing. But in world, people are now working on 150 cc and above. So we have to come up to that, and then again back to the suppliers and again recovery, so that this full supply chain is maintained, and we can be totally Atmanirbhar in this. So there is just a plan which DAE is working on, like in T0.5, we will set up a zone refinement process of HPG crystal and fabrication of 150 cc active volume. And then purification of germanium and growth of detector grade single crystal of diameter 75 mm. And then recovery and recycling will take another around from today onwards if we start. So maybe 22 months or maybe 4 years totally, full indigenous technology and fully indigenous commercial production of HPG detector of volume 150 cc. Maybe in next 5 years we can look forward. So ultimately what we aim is that this is a photograph I am showing from one of the Chinese company where their wafer production was there. So these are all the CZ pullers which I have shown. So this is around like 100 CZ pullers which is controlled by artificial intelligence. And this is like 26 billion US dollar wafer business. So that is what we have to start today so that tomorrow in India we have this kind of facility. So thank you everyone, and this work could not have been possible without the blessings from our parents. Thank you.
Thank you, ma'am, for your brief. We will let us questions. from audience. Any question? You can unmute yourself and ask it, or otherwise you can type the questions in the place.
Question? Hello?
Yes, sir.
Yes, sir. Please go ahead. with your question.
I'm Dushyant Kolmukar from VECC. I saw that you ion implant boron at 25 kV. How do you do that? And
Awesome.
how much depth you can reach with that 25 kV boron?
Sir, with 25 keV boron ions, we are reaching up to around 300 microns in that HPG crystal. And we have an ion implanter from Dan Physics, where we are using boron and boron oxide mix as a target, which is like ionized first, and then this boron ions are accelerated, and then they are deposited on the HPG crystal.
Now you said that the depth is 300 micron,
Yes, sir, 300 micron.
but only you are using 25 kV boron, right? So I think the range will be only 20 to 30 nanometers only.
Actually, sir, we have checked with SEMS and all. So we are going up to that kind of, because that is the dead layer. If it is nanometer, then we won't be able to make the diodes, because after the deposition we are etching and we are covering passivating. So the depth is around 300 micron. That we have checked. Any other question?
Any other questions there?
Anyway, I have the doubt because when you are taking the kV and pardon me.
We can get back to me and later on we can discuss this.
Yes, sir. Thank you. Thank you all. So I thank Dr. Saswati Sharan for really briefing the necessity of growing such as POP germanium crystals, and also she has explained multiple the speed pulling technique and all the devices. A beautiful description for the users who can know about all these fundamentals. So thank you, Dr. Saswati Sharan, for joining us today and briefing us the necessity of this program. On behalf of HBNI, I request our Vice Chancellor, as a token of our love and appreciation, to give a small memento to Dr. Saswati Sharan. with I think from 10:30 onwards, I think our Honorable Prime Minister of India will deliver his speech. So we are trying to connect directly to the link. Please wait for it. After the Prime Minister's speech, we will continue our seminar programs. So in between that, we will try to listen the speech by our Honorable Prime Minister.
सहर्ष आप सभी को सुन भारत के माननीय प्रधानमंत्री महोदय श्री नरेंद्र मोदी जी हमारे साथ जुड़ चुके हैं। हार्दिक अभिनंदन महोदय। जैसा कि विदित है, आज का ये दिन भारत के विकास के प्रति एक अटूट दृढ़ संकल्प का प्रतीक है और भारत के लिए एक उज्जवल समृद्ध भविष्य की यात्रा की ओर आरंभ प्रतीक है। इस समृद्ध यात्रा में हमारे पथ प्रदर्शक भारत के माननीय प्रधानमंत्री महोदय आदरणीय श्री नरेंद्र मोदी जी पूरे देश को स्वावलंबन एवं आत्मनिर्भरता से विभूषित कर रहे हैं। आज का ये कार्यक्रम इसी का प्रतिबिंब है। कार्यक्रम के आरंभ बिंदु को स्पर्श करते हुए मैं अनुरोध करूंगी माननीय रेल, संचार और इलेक्ट्रॉनिकी एवं सूचना प्रौद्योगिकी मंत्री श्री अश्विनी वैष्णव जी से कि आप कृपा करके स्वागत संबोधन प्रस्तुत करें। श्री अश्विनी वैष्णव जी।
परम आदरणीय प्रधानमंत्री श्री नरेंद्र मोदी जी, गुजरात एवं आसाम के माननीय मुख्यमंत्री महोदय, केंद्र एवं राज्य सरकारों में माननीय मंत्री महोदय, टाटा एवं सीजी पावर के अधिकारी, दोनों राज्यों के अधिकारी, ताइवान से जुड़े साथी और कॉलेजेस में जुड़े 30 लाख से अधिक यंग माइंड्स, एक साथ 3 सेमीकंडक्टर यूनिट्स के भूमि पूजन के इस ऐतिहासिक समारोह में आप सभी का हार्दिक स्वागत है। साथियों, किसी भी राष्ट्र के इतिहास में एक ऐसा पीरियड आता है जब उसके भविष्य की नींव रखी जाती है, जब उसके सपने पूरे होते हैं और जब उसे विश्व में नई पहचान मिलती है। और ऐसा तभी संभव होता है जब राष्ट्र का नेतृत्व विजनरी हो, डिसाइसिव हो, फॉरवर्ड लुकिंग हो। आज राष्ट्र में ऐसा नेतृत्व है प्रधानमंत्री श्री नरेंद्र मोदी जी का, डिसाइसिव, विजनरी, फॉरवर्ड लुकिंग, कठिन से कठिन फैसले करने वाले और अपने जीवन का एक एक क्षण राष्ट्र को समर्पित करने वाले प्रधानमंत्री श्री नरेंद्र मोदी जी। साथियों, 1962 से सेमीकंडक्टर इंडस्ट्री को भारत में स्थापित करने का प्रयास चल रहा था। आज सक्सेस मिली है और ये सक्सेस केवल और केवल प्रधानमंत्री श्री नरेंद्र मोदी जी के क्लियर विजन और डिसाइसिव लीडरशिप के कारण मिली है। आज का दिन इतिहास में दर्ज होगा। आने वाली कई जनरेशंस विकसित भारत के निर्माण में आज के दिन को याद करेंगी। आज एक साथ 3 सेमीकंडक्टर यूनिट्स का भूमि पूजन है। इन तीनों प्रोजेक्ट्स और हाल ही में हुए माइक्रोन प्रोजेक्ट, इन 4 को मिलाने से भारत में 4 बड़े सेमीकंडक्टर प्लांट तैयार होंगे और भारत में सेमीकंडक्टर इंडस्ट्री स्थापित होगी। साथियों, सेमीकंडक्टर इंडस्ट्री फाउंडेशनल इंडस्ट्री है। हर वो चीज जिसको ऑन या ऑफ किया जाता है उसमें सेमीकंडक्टर लगता है। चाहे घर में लाइट हो, फैन हो, फ्रिज हो, टीवी हो, स्कूटी हो, बाइक हो, कार हो, ट्रेन हो, एरोप्लेन हो, फैक्ट्री में लगने वाली मशीनें हो, कंप्यूटर हो, मोबाइल फोन हो, हर चीज में सेमीकंडक्टर लगता है। इसीलिए प्रधानमंत्री जी के आत्मनिर्भर भारत के मिशन में सेमीकंडक्टर इंडस्ट्री का बहुत ही महत्वपूर्ण रोल है। और सबसे अधिक खुशी की बात यह है कि इन 4 सेमीकंडक्टर प्लांट्स में से एक प्लांट भारत के नॉर्थ ईस्ट आसाम में आज लग रहा है। कितनी खुशी का वो दिन होगा जब अमेरिका में, यूरोप में, जापान में मेड इन आसाम, मेड इन गुजरात और मेड इन इंडिया सेमीकंडक्टर चिप से बनने वाली कारें दौड़ेंगी, लैपटॉप बनेंगे, कंप्यूटर बनेंगे, मोबाइल फोन चलेंगे। आज के इन तीनों प्लांट और माइक्रोन के सेमीकंडक्टर प्लांट में एक और खासियत है। डबल इंजन की सरकार में कैसे काम तेजी से होता है, ये चारों के चारों प्लांट इसका उदाहरण है। माइक्रोन के प्लांट का माननीय प्रधानमंत्री जी ने अपने अमेरिका की स्टेट विजिट के दौरान जून 2023 में अप्रूवल किया। 90 दिन के अंदर अंदर गुजरात सरकार ने जमीन दी, सारी की सारी परमिशंस दी और फैक्ट्री का काम चालू हुआ। वैसे ही मोदी जी अपना खुद का रिकॉर्ड खुद तोड़ते हैं। टाटा और सीजी पावर के प्लांट 29 फरवरी 2024 में अप्रूव हुए और 15 दिन के अंदर अंदर आज माननीय प्रधानमंत्री जी इन तीनों प्लांट्स का भूमि पूजन कर रहेंगे। ये विश्व में रिकॉर्ड है। ये संभव होता है तभी जब प्रधानमंत्री श्री नरेंद्र मोदी जी जैसा डिसाइसिव लीडर एक देश में आते हैं। राज्य और केंद्र सरकार दोनों ने अपनी पूरी ताकत लगा दी। आज हमारे साथ यंग और एनर्जेटिक 30 लाख से ज्यादा जो साथी वर्चुअली जुड़े हैं। आपसे मैं कहूंगा साथियों, नौजवान साथियों, आपके भविष्य का निर्माण करने वाली ये इंडस्ट्री है। आपके फ्यूचर को सेव करने वाला ये फैसला है और ये फैसला केवल और केवल मोदी जी ले सकते हैं। ये जब आप अपना निर्णय ले आने वाले कुछ दिनों में, तो याद रखना आपके भविष्य का ध्यान केवल और केवल मोदी जी रख सकते हैं। इस बात को आप अपने मन में रखना जब आने वाले कुछ दिनों में आप अपना देश का फैसला लेंगे। इस ऐतिहासिक समारोह में माननीय प्रधानमंत्री जी, आपका और सभी साथियों का हार्दिक अभिनंदन। जय हिंद, भारत माता की जय।
धन्यवाद महोदय। निसंदेह आज माननीय प्रधानमंत्री महोदय के शुभ कर कमलों द्वारा होने वाला ये शिलान्यास आर्थिक एवं प्रौद्योगिकी परिदृश्य में क्रांतिकारी बदलाव लाएगा और देश के सुनहरे भविष्य का निर्माण करेगा। अब मैं चेयरमैन सीजी पावर एंड इंडस्ट्रियल सॉल्यूशंस लिमिटेड श्री विलायन सुबैया से संबोधन का अनुरोध करती हूँ। श्री विलायन सुबैया।
Honorable Prime Minister Narendra Modi ji, Honorable Chief Ministers of Gujarat and Assam, Honorable Ministers Vaishnav ji and Chandrasekhar ji, colleagues, our partners and guests, Namaskaram. 75 years ago, my grandfather manufactured India's first bicycle. That was what the country needed at that time. Times have changed. Semiconductors are the new bicycle. These are the very basis of the modern manufacturing economy. They are critical to India's Atmanirbharta. Today is not just about laying the foundation stones of Tata's 2 plants and our plants, but the very foundation of India's emergence in the modern economy and an announcement of India's arrival on the global semiconductor stage. Why did we have to wait until now for this moment? What Bharat is now witnessing is as revolutionary as independence itself. We are seeing an awakening and a resurgence that India has never ever seen before. This government's ability to foresee what Bharat needs to be a world leader is absolutely unprecedented. Government and industry are collaborating effectively, leveraging each other. मैंने सोचा अगर चिप्स का है इंतजार तो सीजी है तैयार। Until now, Indians have helped other nations strengthen their leadership position in the world order. Brain drain. When I graduated from IIT, 140 students out of my class of 290 left for the US. This will no longer be the case. From now on, we will design for Bharat. We will make for Bharat. We will build Bharat. We are fortunate to have a very strong Japanese partner, Renesas. We asked Renesas who will be leading the initiative from their side. And they said Viresh Patel, who's here with us. मैंने बोला ये वीरेश पटेल तो जापानीज थोड़ा है. But this is the nature of the world today. Or company, Indians are in leading roles, and that's something we ought to be proud of. We are excited to set up this initiative in Gujarat. We come from Tamil Nadu. In Tamil Nadu, we have 79,000 temples. Gujarat has 50,000. It seems that both Tamils and Gujaratis are fond of going to temples. And that's basically because we all understand that there's something much bigger than ourselves. For me as well, yoga and meditation is important. In India, we understand that sadhana and bhakti actually help us become better leaders, help increase our intensity, our energy, our focus. So together, in the presence of Adi Yogi, we will create an intensely powerful semiconductor ecosystem that is built on the foundation of spirituality. I've written a few lines in lighter vein. हम सब हैं एक परिवार, हमारा डोसा आपकी चाट, देश का विकास सेमीकंडक्टर्स के साथ, तेज रफ्तार सीजी के हाथ. To rising India, Jai Hind, Pranam.
Indeed, it's a historic day of silver line in the sky of growth and development of Bharat. और अब समय है चेयरमैन टाटा ग्रुप श्री नटराजन चंद्रशेखरन द्वारा संबोधन का. महोदय, आपसे विनती है कृपा करके अपने विचार प्रस्तुत करें. श्री नटराजन चंद्रशेखरन.
Honorable Prime Minister Shri Narendra Modi ji, thank you for gracing us with your presence on this historic occasion. This event is possible because of your enduring vision to bring the semiconductor industry to the shores of our country. Thank you, sir. Bahut bahut dhanyawad. I am also privileged to welcome Honorable Chief Minister Shri Bhupendra Bhai Patel ji, Honorable Minister Shri Ashwini Vaishnav ji, Honorable Chief Minister Shri Himanta Biswa Sarma ji, and Honorable Minister Shri Rajiv Chandrasekhar ji to this event. Dignitaries from Government of India, Ministry of Electronics and Information Technology, India Semiconductor Mission, governments of both Gujarat and Assam, distinguished guests, ladies and gentlemen, and members of the media. I am thankful to all of you for your presence here in Dholera and Jagi Road, Assam, for the foundation stone laying ceremony of India's first semiconductor fab and the first indigenous semiconductor assembly and test facility. Today is indeed a very, very special day for India and for the Tata Group, with the foundation stone being laid simultaneously for our projects in Dholera and Jagi Road, one in the east and another in the west, 2,500 kilometers apart. These semiconductor manufacturing hubs will have a very lasting impact on the entire nation. The ecosystem from across the globe will mobilize to have India as their preferred semiconductor destination. For our fab, we are very excited to partner with Taiwan's Power Chip Semiconductor Manufacturing Corporation. The executives from PSMC are joining this meeting today on video. They have given us access to a very, very broad portfolio of technology. Our partner is a leading foundry company with very extensive manufacturing experience in running mega fabs. The semiconductor industry is innovation driven. It is another foundational industry, like steel was for, and steel is for physical infrastructure. Semiconductor is the foundational industry for everything digital. We look forward to closely partnering with industry, academic institutions, and every ecosystem player to build semiconductor talent and infrastructure of tomorrow right here in India. We will be creating more than 50,000 jobs in this journey, and this is just the beginning. Today, every major economy is looking for self-sufficiency in semiconductor supply chain. There are three fundamental reasons for this. First, the chip shortages during the pandemic made us all realize the importance of electronics and our dependency on the global supply chain. Second, with the cyber warfare becoming a commonplace, self-sufficiency in semiconductors is a must and a matter of national security. And finally, domestic semiconductor manufacturing ecosystem is a must-have to galvanize the indigenous product ecosystem of tomorrow. In the spirit of the Tata Group and its core value of pioneering, we will deploy our deep customer insights and develop innovative solutions with agility, boldness, and courage. From the very beginning, we have been fortunate to pioneer several businesses, and today our journey of building semiconductor chips has begun. Semiconductor chips have a defining role to play in every industry. Like Minister Vaishnav said, automotive, communications, advanced computing, AI, green tech, industrials, medical devices, defense, consumer electronics, you take every industry, semiconductor chips are very foundational in nature. For the first time, India will have capabilities to serve semiconductor demands of both domestic and global customers with the chips built in our factories in India. I would like to thank you for your trust in the Tata Group as we embark upon this historic journey of India's decade, chips for Viksit Bharat. Finally, in the words of our founder Jamsetji Tata, the community is at the heart of everything that we do. We will build world-class social infrastructure and thriving communities both in Dholera and in Jagi Road in partnership with the Government of Gujarat and Government of Assam. Thank you again for this opportunity, and thank you, Prime Minister, for your leadership and vision and laying the foundation for a developed India. Thank you very much.
धन्यवाद महोदय। वाकई में किसी महत्ता को समझना और फिर उस महत्ता को विकास से जोड़ना ही दूरदृष्टि है। पूरा भारतवर्ष देश के विकास एवं आत्मनिर्भरता को विभूषित करने वाले माननीय प्रधानमंत्री महोदय जी को अपार स्नेह की धरोहर से अलंकृत कर रहा है। आज भारत के माननीय प्रधानमंत्री महोदय के शुभ कर कमलों द्वारा शिलान्यास होने वाले सेमीकंडक्टर यूनिट्स में असम की ATMP यूनिट भी शामिल है। तो आइए जाने असम के माननीय मुख्यमंत्री महोदय कितने आनंद की अनुभूति कर रहे हैं। मेरा सविनय निवेदन है माननीय मुख्यमंत्री असम श्री हेमंत बिस्वा शर्मा जी से कि आप इस शुभ घड़ी में अपने भाव व्यक्त करें। श्री हेमंत बिस्वा शर्मा।
भारत की परम आदरणीय प्रधानमंत्री, विश्व के सबसे लोकप्रिय नेता श्री नरेंद्र मोदी जी, हमारे कैबिनेट मंत्री भारत सरकार की श्री अश्विनी वैष्णव जी, गुजरात के सम्मानीय मुख्यमंत्री भूपेंद्र भाई पटेल जी, टाटा सन्स के चेयरमैन श्री एन चंद्रशेखरन जी, CG पावर के चेयरमैन श्री सुबाया जी, आज हमारे साथ कनेक्ट हुए सारे अतिथिगण, मैं आसाम वासियों का ओर से आप सबको स्वागत करता हूं। प्रधानमंत्री जी, हम जब आसाम में GST का रिजोल्यूशन देश का सबसे पहले पारित किया था, मैं आज भी मेरा याद है आपने हम लोगों को बोला था कि A फॉर असम। आज यही आपका जो वाक्य था, इसको ही आज हमने साकार होते देख रहा हूं। असम को लेके, नॉर्थ ईस्ट को लेके भारतवासियों का मन में एक बहुत बड़ा जियोग्राफिकल बैरियर था। लोग जब कोई भी इंडस्ट्रियल रिवॉल्यूशन होते थे देश में, लोग कभी उत्तर पूर्व को कंसीडर ही नहीं करते थे कि नॉर्थ ईस्ट में भी कुछ करना संभव है। लेकिन प्रधानमंत्री जी, आपका निरंतर उत्तर पूर्व का भ्रमण, आपका आसासी और उत्तर पूर्व के लिए आपका अगाध प्रेम का कारण आज भारत का सेमीकंडक्टर रिवॉल्यूशन का पहला दिन ही आसाम को शामिल होने का सौभाग्य मिला है। आसाम वासी और उत्तर पूर्व आपको हमेशा याद करेगा। एक देश का जो एक नेग्लेक्टेड रीजन था, एक नेग्लेक्टेड रीजन को आपने टेक्नोलॉजिकल रिवॉल्यूशन का पहला चरण में लेके आया। ये हमारे लिए बहुत बहुत गौरव का बात है। मैं पूरा आसाम वासियों का ओर से प्रधानमंत्री जी आपको बहुत बहुत धन्यवाद देता हूं। मेरा मन में कोई भाषा नहीं है, मेरा खाली आज मैं इतना ही बोल सकता हूं। मैं आसाम में ही जन्म लिया हूं, कभी मैं सोचा भी नहीं कि आसाम विल बी द अमंग द वन ऑफ द फर्स्ट स्टेट इन सेमीकंडक्टर रिवॉल्यूशन। ये काम आपका नेतृत्व में संभव हुआ। आसाम वासी आपको कभी नहीं भूलेगा। आसाम का इतिहास में और आसाम का आने वाला पीढ़ी हमेशा आपको याद करेगा, आपका प्रेम का कारण, आपका महानता का कारण। और हमें भी, हम यही आपको आश्वासन देता हूं कि आसाम, जो आपने आसाम का ऊपर ट्रस्ट रिपोर्ट किया है, कॉन्फिडेंस रिपोर्ट किया है, उसका जो एक टेस्ट है, वो टेस्ट में हम खरा उतरने का पूरा कोशिश करूंगा। मैं अश्विनी वैष्णव जी को बहुत बहुत धन्यवाद देता हूं। अश्विनी वैष्णव जी ने हमें मार्गदर्शन किया, कैसे शुरू करना है, कहां से क्या लाना है, सारे हमें पूरा ये समय उन्होंने मार्गदर्शन किया। मैं अश्विनी जी को बहुत बहुत धन्यवाद देता हूं। टाटा सन्स का साथ आसाम का बहुत बड़ा संबंध है। ये आज से ये संबंध नहीं है, ये बहुत दिन पहले से ही हमारा ये संबंध है। और टाटा ने ही ये हिम्मत किया ज्योग्राफिकल बैरियर को तोड़ने के लिए। मैं चंद्रशेखरन जी और तमाम टाटा ग्रुप को धन्यवाद देता हूं। और मैं आपको आश्वासन देता हूं कि आप एकदम बहुत बढ़िया आसाम में इकोसिस्टम मिलेगा। और आपको कभी, आपने जो ये सिद्धांत लिया, इसका कारण आप कभी रिग्रेट नहीं करेगा। आपको खुशी होगा, आपको अच्छा लगेगा कि यू हैव चूजन ए करेक्ट डेस्टिनेशन एंड चूजिंग नॉर्थ ईस्ट, you have contributed immensely for the development of this great region and great nation. प्रधानमंत्री जी, हमारा सामने लाखों लोग मौजूद हैं, सब आपको दोबारा अभिवादन करते हैं। और आसाम का इतिहास हमेशा एक आपको युग पुरुष का नाते आपको हमेशा याद करेगा। मेरा कोई भाषा नहीं है, मैं खाली आपको धन्यवाद देता हूं दिल से, आसाम वासियों का दिल से। भगवान आपको लंबी आयु दे और भारत को विश्व गुरु बनाने का जो सपना है, आपका मार्गदर्शन में, आपका हाथ में ही भारत मां विश्व गुरु बने, यही मेरा कामना है, यही हम लोग का आशा है। और हमेशा आप ऐसे ही उत्तर पूर्व को आशीर्वाद देते रहे, आसाम को आशीर्वाद देते रहे। बहुत बहुत धन्यवाद प्रधानमंत्री जी, बहुत बहुत धन्यवाद। जय हिंद, वंदे मातरम।
इस शुभ बेला के उत्साह की तरंगे चहु और आभास की जा सकती है और पूरे देश को इस गौरव की अनुभूति देने हेतु एक बार पुनः मैं शिल्पा भावना करबद्ध रूप में प्रणाम करना चाहूंगी हमारे देश के माननीय प्रधानमंत्री महोदय को। विकास की इस अविरल बेला में गुजरात के धौलेरा में सेमीकंडक्टर फैब विद 50,000 WSPM कैपेसिटी एवं सानंद में सेमीकंडक्टर APMP यूनिट फॉर स्पेशलाइज्ड चिप्स का शिलान्यास अब से कुछ ही देर में माननीय प्रधानमंत्री महोदय द्वारा किया जाएगा। तो गुजरात की ये धरती इस आरंभवर्ती क्षण को किस प्रकार संजोए है, आइए जानते हैं माननीय मुख्यमंत्री गुजरात श्री भूपेंद्र भाई पटेल जी के शब्दों में। माननीय, आपसे अनुरोध है कि कृपा करके उपस्थित गणों को संबोधित करें। श्री भूपेंद्र भाई पटेल।
भारत के सर्वप्रथम सेमीकंडक्टर फैब प्रोजेक्ट के भूमि पूजन समारोह में हमारे बीच वर्चुअल माध्यम से उपस्थित वैश्विक नेता, विकास पुरुष, आदरणीय प्रधानमंत्री श्री नरेंद्र भाई मोदी साहब, आसाम के जनप्रिय मुख्यमंत्री श्री हेमंत बिस्वा जी, हमारे साथ मंच पर भी उपस्थित केंद्रीय मंत्री श्री अश्विनी जी वैष्णव, डॉक्टर महेंद्र भाई मुजपरा, टाटा ग्रुप के चेयरमैन श्री एन चंद्रशेखर जी, सीजी पावर के चेयरमैन श्री बेलिया सुबैया जी, सीईओ श्री डॉक्टर रणधीर ठाकुर, उपस्थित सभी महानुभाव, सभी वर्चुअल माध्यम से जुड़े सभी साथी मंत्रीगण, सभी धारा सभ्य श्री और वाला प्यारे स्टूडेंट, इंडिया टेकेड चीफ फॉर विकसित भारत के इस कार्यक्रम के माध्यम से प्रधानमंत्री जी गुजरात को भारत का सेमीकंडक्टर हब बनाने वाली परियोजनाओं की आधारशिला रखने के लिए हमारे साथ उपस्थित है। मैं एक बार फिर माननीय प्रधानमंत्री जी का इस विशेष उपहार के लिए हृदय से आभार व्यक्त करता हूं और स्वागत करता हूं। हम सब इस बात के साक्षी हैं कि माननीय प्रधानमंत्री श्री नरेंद्र भाई की विजनरी लीडरशिप में भारतीय उद्योग हर दिन नई ऊंचाई हासिल कर रहा है। आत्मनिर्भर भारत के संकल्प के तहत उनके प्रयासों से आज हम ऐसे कई कार्यों को संभव होते हुए देख रहे हैं जो कभी हम मुश्किल लगा करते थे। सेमीकंडक्टर मैन्युफैक्चर भी उन्हीं सेक्टर में से एक है। प्रधानमंत्री जी कहते हैं कि समस्या और संभावना में सिर्फ सोच का ही फर्क है और समस्या को संभावनाओं में बदलना ही मोदी जी की गारंटी है। भारत में टेक्नोलॉजी का विस्तार तेजी से बढ़ रहा है। हेल्थ, एग्रीकल्चर, लॉजिस्टिक ऐसे कई सेक्टर्स में स्मार्ट टेक्नोलॉजी का उपयोग बढ़ रहा है। इंटरनेट ऑफ थिंग्स और आर्टिफिशियल इंटेलिजेंस हमारी डे टू डे लाइफ में शामिल हो गए हैं। इन सभी मॉडर्न टेक्नोलॉजी के मूल में सेमीकंडक्टर चिप और इलेक्ट्रॉनिक गैजेट ही है और विश्व को रिलायबल चिप सप्लाई चेन की जरूरत है। प्रधानमंत्री जी के दिशा दर्शन में सेमीकंडक्टर मैन्युफैक्चरिंग सेक्टर में गुजरात को भारत का केंद्र बनाने के संकल्प के साथ हम आगे बढ़ रहे हैं। प्रधानमंत्री जी के विकसित भारत के लिए विकसित गुजरात का जो विजन दिया है उसे साकार करने के लिए गुजरात प्रतिबद्ध है। गुजरात के पास प्रधानमंत्री जी के इसी विजन को जमीन पर उतारने की अपार क्षमता है। सेमीकंडक्टर जैसे उभरते सेक्टर को प्रमोट करने के लिए गुजरात देश का पहला राज्य है जिसे डेडिकेटेड सेमीकंडक्टर पॉलिसी बनाई है। हमारी सेमीकंडक्टर पॉलिसी की खास बात यह है कि भारत सरकार द्वारा अप्रूव्ड सेमीकंडक्टर प्रोजेक्ट्स को अपने आप ही गुजरात में अप्रूवल मिल जाती है। धौलेरा में विकसित हो रहा सेमिकॉन सिटी भी भारत में एकमात्र डेस्टिनेशन है जहां सेमीकंडक्टर सेक्टर से जुड़ी सभी जरूरत का ख्याल रखा जा रहा है। विश्व की सेमीकंडक्टर मैन्युफैक्चरिंग कंपनियां गुजरात की इन्हीं फैसिलिटीज के आकर्षित भी हो रहे हैं। माइक्रोन कंपनी के बाद सेमीकंडक्टर से जुड़े 2 प्लांट की आधारशिला रखी जा रही है। ये हम सभी के लिए गौरव के क्षण हैं। सेमीकंडक्टर और इलेक्ट्रॉनिक सेक्टर में मिलने वाली सभी निवेश अवसरों का लाभ लेने के लिए हमने एक नोडल एजेंसी गुजरात स्टेट इलेक्ट्रॉनिक मिशन को ऑपरेशनल किया है। आज धौलेरा में टाटा इलेक्ट्रॉनिक्स प्राइवेट लिमिटेड और सानंद जीआईडीसी में सीजी पावर अपने यूनिट स्थापित करने जा रहे हैं। आप सभी को यह जानकर खुशी होगी, जनवरी 2024 में आयोजित वाइब्रेंट गुजरात ग्लोबल समिट में श्री एन चंद्रशेखर जी ने घोषणा की थी कि टाटा ग्रुप धौलेरा में एक विशाल सेमीकंडक्टर फैब यूनिट स्थापित करेगा और ठीक 2 महीने के बाद हम सभी इस समारोह के साक्षी बन रहे हैं। इतने ही कम समय में इस यूनिट की स्थापना का काम शुरू हो जाना, यह प्रधानमंत्री जी के नेतृत्व में डबल इंजन सरकार की उपलब्धि का जीता जागता उदाहरण है। इन दोनों यूनिट्स की स्थापना से लगभग 50,000 से अधिक रोजगारी के अवसर खुलेंगे। गुजरात में मैन्युफैक्चरिंग होने वाले इस सेमीकंडक्टर चिप का उपयोग न केवल भारत में मौजूद इलेक्ट्रिकल व्हीकल इंडस्ट्रीज, टेलीकॉम, ऑटोमेटिव, डिस्प्ले और पावर इलेक्ट्रॉनिक्स जैसे सेक्टर में होगा, बल्कि साथ ही ग्लोबल सप्लाई चेन का भी हम हिस्सा बनेंगे। ये यूनिट्स हमारे देश में चिप फैब्रिकेशन में अपनी क्षमता को विकसित करेंगे और भारत को विश्व स्तर पर सेमीकंडक्टर चिप सप्लाई चेन में शामिल भी करेंगे। धौलेरा में उपलब्ध ये इंडस्ट्रियल फैसिलिटीज सेमीकंडक्टर जैसे ग्लोबल डिमांड वाले सेक्टर्स के लिए बेस्ट स्ट्रेटेजिकल लोकेशन है, ऐसा मेरा मानना है। इसके अलावा अहमदाबाद और धौलेरा को जोड़ने वाले एक्सप्रेस हाईवे, रीजनल रेल और धौलेरा का इंटरनेशनल एयरपोर्ट सेमीकंडक्टर सेक्टर से पूरे इकोसिस्टम को जरूरी लॉजिस्टिक उपलब्ध कराएंगे। प्रधानमंत्री जी अक्सर कहते हैं कि मेक इन इंडिया, मेक फॉर द वर्ल्ड। इनके इस विचार को वास्तविक रूप देने के दिशा में भारत जल्द ही सेमीकंडक्टर सेक्टर में ग्लोबल प्लेयर बनकर उभरेगा और गुजरात इसमें सबसे बड़ा कंट्रीब्यूटर स्टेट बनेगा। इस विश्वास के साथ मैं अपनी वाणी को विराम देता हूँ। भारत माता की जय, वंदे मातरम, जय जय गरवी गुजरात।
धन्यवाद महोदय। भारत में विनिर्माण पारिस्थितिकी तंत्र को शक्ति देने हेतु अब समय है प्रधानमंत्री महोदय श्री नरेंद्र मोदी जी के कस्तूरी करों द्वारा तीनों सेमीकंडक्टर फैसिलिटीज के शिलान्यास का। मैं अनुरोध करती हूं माननीय प्रधानमंत्री जी से कि आप कृपा करके रिमोट के बटन के माध्यम से तीनों सेमीकंडक्टर फैसिलिटीज का शिलान्यास कर अनुग्रहित करें। धौलेरा गुजरात की टीईपीएल फैब फैसिलिटी का शिलान्यास भारत के माननीय प्रधानमंत्री जी द्वारा किया जा चुका है और अब हो रहा है मोरेगांव असम की टीईपीएल ओसेट फैसिलिटी का शिलान्यास। आरंभ के इस चंदन पर संपूर्ण राष्ट्र की शुभेच्छा। और अब सानंद गुजरात के सीजी पावर ओसेट फैसिलिटी के शिलान्यास के हम सभी साक्षी बन रहे हैं। इति शुभम। अब प्रस्तुत है इन परियोजनाओं पर बनी लघु चलचित्र।
प्रधानमंत्री नरेंद्र मोदी की विजनरी लीडरशिप में भारत आज जिस स्केल और स्पीड पर काम कर रहा है वो अभूतपूर्व है। इसकी शानदार मिसाल है हमारा अपना सेमीकंडक्टर फैब, जिसका सपना देश ने देखा था 1962 में, यानी 62 साल पहले। बीते 6 दशकों में कुछ कोशिशें हुई, लेकिन इच्छा शक्ति की कमी के कारण देश का ये सपना कभी साकार नहीं हो सका। वक्त ने करवट तब ली जब देश ने जननायक प्रधानमंत्री नरेंद्र मोदी को जिम्मेदारी सौंपी विकसित भारत के निर्माण की। करोड़ों देशवासियों की आकांक्षाओं के साथ आत्मनिर्भर भारत के संकल्प को जोड़ते हुए प्रधानमंत्री नरेंद्र मोदी ने जब एक ढर्रे पर चल रहे देश का गियर बदला तो भारत ये सेमीकंडक्टर फैब का सपना साकार हो उठा।
भारत सेमीकंडक्टर इंडस्ट्री के लिए एक अच्छा एनर्जी कंडक्टर बनने के लिए हर चेकबॉक्स को टिक कर रहा है।
भारत आज अपने टेक फ्यूचर को जिस स्पीड के साथ आकार दे रहा है उसका एक और उदाहरण है माइक्रोन। जून 2023 में जिसकी घोषणा होने के 90 दिन के भीतर ही गुजरात के सानंद में प्रोजेक्ट पर काम शुरू कर दिया गया था और अब इस साल दिसंबर तक पहली चिप का निर्माण होने की संभावना है। अपने इन चारों मेगा प्रोजेक्ट्स के साथ भारत ने चौथी औद्योगिक क्रांति इंडस्ट्री 4.0 में अपनी अहम भागीदारी तो सुनिश्चित कर ही ली है, लेकिन साथ ही चिप मेकिंग के क्षेत्र में ग्लोबल लीडर भी बनने जा रहा है।
वन अर्थ, वन फैमिली, वन फ्यूचर। भारत को सेमीकंडक्टर मैन्युफैक्चरिंग हब बनाने के पीछे भी हमारी यही भावना है। भारत की स्किल, भारत की कैपेसिटी, भारत की कैपेबिलिटी का पूरी दुनिया को लाभ हो, यही भारत की इच्छा है।
आज 3 सेमीकंडक्टर मैन्युफैक्चरिंग यूनिट्स के ग्राउंड ब्रेकिंग समारोह के साथ ही मेक इन इंडिया और आत्मनिर्भर भारत को एक नई बुलंदी मिल रही है। सरकार इन प्रोजेक्ट्स को 50% की बड़ी आर्थिक सहायता देगी। गुजरात के धोलेरा में हर महीने 50,000 वेफर्स बनाने वाला सेमीकंडक्टर फैब प्रोजेक्ट, असम के मोरीगांव में हर दिन 48 मिलियन चिप्स बनाने वाला आउटसोर्स्ड सेमीकंडक्टर असेंबली एंड टेस्ट ओसैट प्रोजेक्ट और गुजरात के सानंद में हर दिन 15 मिलियन चिप्स बनाने वाला आउटसोर्स्ड सेमीकंडक्टर असेंबली एंड टेस्ट ओसैट प्रोजेक्ट। इन तीनों प्रोजेक्ट्स के साथ सरकार 1,26,000 करोड़ रुपए की लागत से देश में सेमीकंडक्टर इकोसिस्टम की एक सुदृढ़ आधारशिला रख रही है। अमृत काल में भारत के सेमीकंडक्टर सेक्टर की विकास यात्रा तेज गति से जारी रहेगी और भारत सेमीकंडक्टर मैन्युफैक्चरिंग का ग्लोबल हब बनकर उभरेगा।
वाकई आज के इस अभूतपूर्व शिलान्यास में माननीय प्रधानमंत्री महोदय श्री नरेंद्र मोदी जी ने भारत के पूरब और पश्चिम छोर को मिलाकर आज एक ऐसे भविष्य की नींव रखी है जिस पर विकसित भारत पल्लवित होगा। और इस उपवन के उद्यानपाल भारत के माननीय प्रधानमंत्री महोदय जी के स्वागत का जय घोष करते हुए मैं आदरणीय श्री नरेंद्र मोदी जी से संबोधन के लिए अनुरोध करती हूँ। लेडीज एंड जेंटलमैन, श्री नरेंद्र मोदी जी।
नमस्कार। केंद्रीय मंत्रिमंडल के मेरे सहयोगी श्री अश्विनी वैष्णव जी, राजीव चंद्रशेखर जी, असम और गुजरात के मुख्यमंत्री, टाटा ग्रुप के चेयरमैन श्री एन चंद्रशेखरन, सीजी पावर के चेयरमैन वेलायन सुबैया जी, केंद्र, राज्य एवं इंडस्ट्री से जुड़े अन्य सभी वरिष्ठ महानुभाव, देवी और सज्जनों, आज का ये दिन ऐतिहासिक है। आज हम इतिहास भी रच रहे हैं और उज्जवल भविष्य की तरफ एक बहुत बड़ा मजबूत कदम भी उठा रहे हैं। आज सेमीकंडक्टर मैन्युफैक्चरिंग से जुड़े करीब 1.25 करोड़ रुपए के 3 बड़े प्रोजेक्ट का शिलान्यास हुआ है। गुजरात के धोलेरा और साणंद में सेमीकंडक्टर फैसिलिटी हो, असम के मोरीगांव में सेमीकंडक्टर फैसिलिटी हो, ये भारत को सेमीकंडक्टर मैन्युफैक्चरिंग का एक बड़ा ग्लोबल हब बनाने में मदद करेगी। मैं सभी देशवासियों को
इस महत्वपूर्ण पहल के लिए, एक महत्वपूर्ण शुरुआत के लिए, एक मजबूत कदम के लिए इस आयोजन को लेकर के बहुत बहुत बधाई देता हूं। आज इस कार्यक्रम में ताइवान के हमारे साथी भी वर्चुअल रूप से शामिल हुए हैं। मैं भी भारत के इन प्रयासों से काफी उत्साहित हूं। साथियों, इस अभूतपूर्व अवसर पर हमारे साथ देश के 60,000 से ज्यादा कॉलेज, यूनिवर्सिटीज और एजुकेशन इंस्टीट्यूट भी जुड़े हुए हैं। ये अपने आप में एक रिकॉर्ड ही है। मैंने मंत्रालय से विशेष आग्रह किया था कि आज का ये कार्यक्रम देश के नौजवानों के सपनों का कार्यक्रम है और इसलिए ज्यादा से ज्यादा संख्या में आज इस कार्यक्रम में हमारे युवाओं को जोड़ना चाहिए। आज का आयोजन भले ही सेमी कंडक्टर प्रोजेक्ट की शुरुआत का हो, लेकिन भविष्य के भारत के असली स्टेक होल्डर्स अगर कोई है तो ये मेरे सामने बैठे हुए मेरे युवा, मेरे नौजवान, मेरे स्टूडेंट्स, यही मेरी भारत की शक्ति है। इसलिए मेरी इच्छा थी कि भारत के छात्र इस ऐतिहासिक क्षण के साक्षी जरूर बने। आज वो देख रहे हैं कि भारत किस तरह प्रगति के लिए, आत्मनिर्भरता के लिए ग्लोबल सप्लाई चेन में अपनी मजबूत उपस्थिति के लिए चौतरफा काम कर रहा है। इन प्रयासों से उनका भी आत्मविश्वास बढ़ेगा और आत्मविश्वास से भरा युवा कहीं भी हो, वो अपने देश का भाग्य बदल देता है। मैं इस कार्यक्रम में देश के कोने कोने से शामिल प्रत्येक छात्र का स्वागत करता हूं, उनका अभिनंदन करता हूं। फ्रेंड्स, 21वीं सदी टेक्नोलॉजी ड्रिवन सेंचुरी है और इलेक्ट्रॉनिक चिप के बिना उसकी कल्पना भी नहीं की जा सकती। मेड इन इंडिया चिप, डिजाइन इन इंडिया चिप भारत को आत्मनिर्भरता की तरफ से ले जाने में, आधुनिकता की तरफ ले जाने में ये बहुत बड़ा सामर्थ्य पैदा करेगी। पहली, दूसरी और तीसरी औद्योगिक क्रांति के समय भारत अनेक कारणों से पीछे रह गया था, लेकिन अब भारत इंडस्ट्री 4.0 चौथी औद्योगिक क्रांति के नेतृत्व के इरादे से आत्मविश्वास के साथ आगे बढ़ रहा है। हम एक पल भी गंवाना नहीं चाहते और हम इस दिशा में कितनी तेजी से काम कर रहे हैं, आज का ये कार्यक्रम इसका भी एक उदाहरण है। हमने 2 साल पहले सेमीकंडक्टर मिशन शुरू करते हुए इनिशिएटिव लेने की घोषणा की। इसके कुछ ही महीनों में हमारे पहले एमओयू साइन हो गए और आज सिर्फ कुछ महीनों के भीतर हम 3 प्रोजेक्ट्स का शिलान्यास कर रहे हैं। इंडिया कमिट्स, इंडिया डिलीवर्स एंड डेमोक्रेसी डिलीवर्स। साथियों, दुनिया के बस कुछ देश ही आज सेमीकंडक्टर्स की मैन्युफैक्चरिंग कर रहे हैं और कोरोना ने हमें ये सबक दिया है कि दुनिया को एक रिलायबल और रेजिलियंट सपोर्ट सप्लाई चेन की सख्त जरूरत है। भारत इसमें एक बहुत बड़ी भूमिका निभाने के लिए तत्पर है। भारत पहले ही एक स्पेस, न्यूक्लियर और डिजिटल पावर है। आने वाले समय में हम सेमीकंडक्टर सेक्टर से जुड़े प्रोडक्ट्स का कॉमर्शियल प्रोडक्शन करेंगे। वो दिन दूर नहीं जब भारत इसमें भी एक ग्लोबल पावर बनेगा। भारत अभी जो फैसले ले रहा है, जो नीतियां बना रहा है, उसका भी हमें स्ट्रेटेजिक एडवांटेज मिलेगा। हमने ईज ऑफ डूइंग बिजनेस को बढ़ावा दिया है, हमने कानूनों को आसान किया है। बीते वर्षों में हमारी सरकार ने 40,000 से ज्यादा कंप्लायंसेस खत्म किए हैं। भारत में निवेशकों के लिए एफडीआई के नियम भी आसान हुए हैं। डिफेंस, इंश्योरेंस और टेलीकॉम जैसे सेक्टर्स में एफडीआई पॉलिसी को और लिबरल किया गया है। हाल के वर्षों में हमने इलेक्ट्रॉनिक्स और हार्डवेयर मैन्युफैक्चरिंग से उसमें भी अपनी पोजीशन को और मजबूत किया है। लार्ज स्केल इलेक्ट्रॉनिक्स मैन्युफैक्चरिंग और आईटी हार्डवेयर के लिए पीएलआई स्कीम्स हो, इलेक्ट्रॉनिक कंपोनेंट्स के लिए स्कीम्स हो या फिर इलेक्ट्रॉनिक्स मैन्युफैक्चरिंग क्लस्टर्स हो, इन सभी में भारत ने इंसेंटिव्स देकर इलेक्ट्रॉनिक्स इकोसिस्टम्स को तरक्की के नए अवसर दिए हैं। आज भारत पूरी दुनिया का दूसरा सबसे बड़ा मोबाइल फोन मैन्युफैक्चरर है। कुछ समय पहले हमने नेशनल क्वांटम मिशन की भी शुरुआत की है। इनोवेशन को बढ़ावा देने के लिए नेशनल रिसर्च फाउंडेशन की स्थापना भी की गई है। इंडिया एआई मिशन का भी तेजी से विस्तार होने जा रहा है। यानी हम सिर्फ टेक्नोलॉजी एडॉप्शन नहीं, टेक्नोलॉजी एडवांसमेंट के रास्ते पर भी बढ़ रहे हैं। साथियों, सेमीकंडक्टर इंडस्ट्री का सबसे ज्यादा लाभ अगर किसी को मिलने वाला है, सेमीकंडक्टर इंडस्ट्री कम्युनिकेशन से ट्रांसपोर्टेशन तक कई सेक्टर जुड़े होते हैं। ग्लोबल इकोनॉमी में भी इस इंडस्ट्री से कई बिलियन डॉलर का रेवेन्यू और एम्प्लॉयमेंट जनरेशन होता है। यानी चिप मैन्युफैक्चरिंग सिर्फ एक इंडस्ट्री मात्र नहीं है, ये विकास का वो द्वार खोलती है जो असीम संभावनाओं से भरा हुआ है। इस सेक्टर से ना सिर्फ भारत में रोजगार के नए अवसर बनने वाले हैं, बल्कि टेक्नोलॉजिकल एडवांसमेंट्स के क्षेत्र में भी बड़ी प्रगति होने वाली है। आज दुनिया भर की सेमीकंडक्टर चिप के पीछे जो डिजाइन है और उस डिजाइन के पीछे का जो दिमाग है, वो दिमाग अधिकांश भारत के युवा का ही है। इसलिए आज जब भारत सेमीकंडक्टर मैन्युफैक्चरिंग के क्षेत्र में आगे बढ़ रहा है, तो हम टैलेंट इकोसिस्टम की इस साइकिल को एक प्रकार से कंप्लीट कर रहे हैं। आज अभी इस कार्यक्रम में हमारे साथ जुड़े हुए युवा ये जानते हैं कि कैसे आज देश में उनके लिए नई नई संभावनाएं बन रही है, नए अवसर बन रहे हैं। स्पेस का सेक्टर हो, मैपिंग का सेक्टर हो, भारत ने अपने युवाओं के लिए इन सेक्टर्स को पूरी तरह खोल दिया है। हमारी सरकार ने स्टार्टअप इकोसिस्टम को जो इंसेंटिव दिए हैं, जो प्रोत्साहन दिया है, वो अभूतपूर्व है। और इसी का कमाल है कि इतने कम वर्षों में भारत दुनिया का तीसरा सबसे बड़ा स्टार्टअप इकोसिस्टम बन गया है। अब आज के इस आयोजन के बाद सेमीकंडक्टर सेक्टर में भी हमारे स्टार्टअप के लिए नए मौके बनने जा रहे हैं। मुझे विश्वास है कि ये नई शुरुआत हमारी युवा पीढ़ी को एडवांस टेक्नोलॉजी जॉब से जुड़ने की नई अपॉर्चुनिटी देगी। साथियों, आपको याद होगा, लाल किले से मैंने कहा था, यही समय है, सही समय है। जब हम इस भावना के साथ नीतियां बनाते हैं, निर्णय लेते हैं, तो नतीजे भी मिलते हैं। भारत अब पुरानी सोच और पुरानी अप्रोच ये छोड़ चुका है, बहुत आगे निकल गया है। भारत अब तेज गति से निर्णय ले रहा है, नीतियां बना रहा है। हम पहले ही सेमीकंडक्टर मैन्युफैक्चरिंग में कई दशक खो चुके हैं, लेकिन अब हमें एक पल भी गंवाना नहीं है और अब ऐसा नहीं होगा। भारत ने सबसे पहले 60 के दशक में सेमीकंडक्टर मैन्युफैक्चरिंग का सपना देखा था, इस बारे में सोचा था। लेकिन इस सपने के बाद भी, इस सोच के बाद भी तब की सरकारें उन अवसरों का लाभ नहीं ले पाई। इसके सबसे बड़े कारण थे इच्छा शक्ति की कमी, अपने संकल्पों को सिद्धि में बदलने के लिए प्रयास की कमी और देश के लिए दूरगामी फैसले लेने की क्षमता की कमी। इस वजह से वर्षों तक भारत का सेमीकंडक्टर बनाने का सपना बस सपना ही रह गया। उन दशकों में जो लोग सरकार में रहे वो भी सोचते थे कि अरे जल्दी क्या है, समय आएगा तब हो जाएगा। सरकारों को लगता था कि ये तो भविष्य की जरूरत है, इसका समाधान अभी क्यों करना। वो लोग देश की प्रायोरिटीज को भी बैलेंस नहीं कर पाए, देश के सामर्थ्य को भी समझ नहीं पाए। उन लोगों को लगा कि भारत तो गरीब देश है, भारत सेमीकंडक्टर मैन्युफैक्चरिंग जैसी हाईटेक चीज को कैसे मैनेज कर पाएगा। वो लोग भारत की गरीबी की आड़ में आधुनिक जरूरत के ऐसे हर इन्वेस्टमेंट को नजरअंदाज करते रहे। वो हजारों करोड़ के घोटाले कर लेते थे, लेकिन सेमीकंडक्टर मैन्युफैक्चरिंग पर हजारों करोड़ रुपए इन्वेस्ट नहीं कर पाए। ऐसी सोच के साथ किसी देश का विकास नहीं हो सकता। इसलिए हमारी सरकार फॉरवर्ड लुकिंग सोच और फ्यूचरिस्टिक अप्रोच के साथ काम कर रही है। आज हम सेमीकंडक्टर मैन्युफैक्चरिंग में उन एम्बिशंस के साथ बढ़ रहे हैं जो विकसित देशों के साथ कॉम्पीट कर सके। हमारे देश की सारी प्राथमिकताओं का भी ध्यान रखा है। एक तरफ हम गरीबों के पक्के घर बनवा रहे हैं, तो दूसरी तरफ भारत रिसर्च को बढ़ावा देने के लिए भी लाखों करोड़ रुपए खर्च कर रहा है। एक तरफ हम विश्व का सबसे बड़ा सैनिटेशन मूवमेंट चला रहे हैं, वहीं दूसरी ओर भारत में सेमीकंडक्टर मैन्युफैक्चरिंग पर भी आगे बढ़ रहा है। हम एक तरफ देश में तेजी से गरीबी कम कर रहे हैं और दूसरी तरफ भारत में आधुनिक इंफ्रास्ट्रक्चर का भी निर्माण कर रहे हैं, देश को आत्मनिर्भर भी बना रहे हैं। सिर्फ 2024 में ही अब तक 12 लाख करोड़ रुपए से ज्यादा की योजनाओं का शिलान्यास और लोकार्पण कर चुका है। कल ही हमने पोखरण में 21वीं सदी के भारत के आत्मनिर्भर डिफेंस सेक्टर की झांकी देखी। वो दिन पहले ही भारत ने 2 दिन पहले ही भारत ने अग्नि 5 के रूप में भारत को दुनिया के एक्सक्लूसिव क्लब में शामिल होते देखा। 2 दिन पहले ही देश की खेती में ड्रोन क्रांति की शुरुआत हुई। नमो ड्रोन दीदी योजना के तहत हजारों ड्रोन महिलाओं को सौंपे गए। गगनयान को लेकर भी भारत की तैयारी और तेजी आई है। हाल में ही देश ने को अपना पहला मेड इन इंडिया फास्ट ब्रीडर न्यूक्लियर रिएक्टर मिला है। ये सारे प्रयास, ये सारे प्रोजेक्ट्स भारत को विकसित होने के लक्ष्य के और निकट ले जा रहे हैं, तेज गति से ले जा रहे हैं। और निश्चित तौर पर आज के इन 3 प्रोजेक्ट की भी इसमें बड़ी भूमिका होगी। और साथियों, आप जानते हैं आज चारों तरफ एआई की भी उतनी ही चर्चा है। भारत की टैलेंट आज एआई की दुनिया में उसका बहुत बड़ा दबदबा है। आपने देखा होगा पिछले 1-2 सप्ताह से मेरे जितने भी भाषण होते हैं, कुछ युवा नौजवान मेरे पास आए। उन्होंने कहा, साहब हम आपकी एक एक बात हर भाषा में गांव-गांव पहुंचाना चाहते हैं। उन्होंने एआई टूल का उपयोग किया और आज मेरा हर भाषण आप अपनी अपनी भाषा में कुछ ही समय के बाद सुनना शुरू कर दोगे। यानी किसी को तमिल सुनना है, किसी को पंजाबी सुनना है, किसी को बंगाली सुनना है, किसी को असमिया, उड़िया, जो भी सुनना है। ये एआई का कमाल ये मेरे देश के नौजवान कर रहे हैं और मैं तो ऐसे नौजवान टीम का आभारी हूं कि उन्होंने मेरे लिए इतना बढ़िया एआई के जनरेटेड मेरी स्पीचेस को, मेरे भाषणों को हिंदुस्तान की सभी भाषाओं में इंटरप्रिटेशन के साथ पहुंचाने का जो प्रयास किया है, मेरे लिए बड़ा आनंद का, खुशी का विषय बना है। और देखते ही देखते सभी लैंग्वेज में भी हमारी बात एआई के माध्यम से पहुंचेगी। कहने का तात्पर्य यह है कि भारत के नौजवानों का जो सामर्थ्य है, उनको अवसर चाहिए। और ये सेमीकंडक्टर का हमारा इनिशिएटिव देश के नौजवानों के लिए बहुत बड़ा अवसर लेकर आया है। साथियों, एक बार फिर मैं आप सभी को बहुत बहुत शुभकामनाएं देता हूं और मैं हेमंता जी की इस बात से बहुत सहमत हूं कि नॉर्थ ईस्ट में कभी किसी ने सोचा नहीं था कि इतने बड़े इनिशिएटिव लिए जा सकते हैं। हमने ये तय किया है और मैं तो मानता हूं साउथ ईस्ट एशिया से के साथ हमारा जो जुड़ाव बढ़ रहा है, तो मेरा नॉर्थ ईस्ट साउथ ईस्ट एशिया के साथ जुड़ने का सबसे ताकतवर क्षेत्र बनने वाला है। आप सब इसको देख रहा हूं और मैं इसकी शुरुआत देख रहा हूं। तो मैं आसाम के लोगों को, नॉर्थ ईस्ट के लोगों को आज सबसे ज्यादा शुभकामनाएं देता हूं, सबसे ज्यादा बधाई देता हूं। साथियों, आप सब ऐसे ही भारत की प्रगति को एक नई शक्ति देने के लिए जुड़ते रहिए, आगे बढ़ते रहिए। मोदी की गारंटी आपके लिए है, आपके भविष्य के लिए है, आपको साथ देने के लिए है। बहुत बहुत धन्यवाद।
Welcome back. We are going to have our second lecture by Mr. Gupta. For tonight, you hear us? So anyone participant can please respond. Am I audible? Sound. For tonight, anybody please respond? Can hear me?
Yes, sir, I have unmuted already.
There?
Yes, sir. Now it is off. Now it is on.
Okay.
Red is off. Yes.
Take your mobile. We call somebody there, mobile. Maybe just to put up. Yes, now the is over.
Dr. Mukesh Ranjan.
Hello?
Sir, can you hear me? Please.
Yeah, I can hear you.
Okay, we will start. We are waiting for some response from the audience.
Okay.
So welcome back. Our next lecture 2 is on high purity silicon for semiconductor and radiation industry. It's going to be delivered by Sri Sulabh Gupta, Scientific Officer E, Heavy Water Division BRC. His personal field of interest is production of semiconductor grade silicon vapor, production of high purity polysilicon from sand. Sri Sulabh Gupta is engaging in the design, development, and setting up of technologies for the production of high purity monocrystalline silicon. He is currently involved in setting up a facility for 5,000 kg per annum of high purity mono silicon production plant. The technology at pilot scale has been demonstrated and patented radiation detectors have been fabricated from vapor produced at BRC. The present technology has been demonstrated up to 4-inch silicon crystal. The vapor produced in-house or at par with the commercially available vapors. It was published one paper in a peer-reviewed international journal. The may now request Sri Sulabh Gupta to present his lecture on high purity silicon for semiconductor and radiation industry. Welcome, sir. Please go ahead.
Good morning. Thank you for the introduction. So starting with the high purity silicon. So silicon is the major semiconductor which is used worldwide, and depending on the purity of the silicon wafers that we are producing, it has various applications. The first application which you will be using right now is integrated circuits in the form of processors in your mobiles or in your laptops. Some of the applications for a low purity material would be in solar cells, where we are generating solar power. And for high purity, very high purity is used in radiation detection. And some other applications would be in high power devices, manufacturing of high power devices. So these all are possible because of the very large availability of silicon in our core. Basically sand, which is silica SiO2, which is abundantly available in the earth crust. So there are two types of silicon semiconductors that you can manufacture from silicon material. One of them is the extrinsic one, which is doped, either P-type or N-type, depending on the impurity of the dopant. And second would be intrinsic. The intrinsic is basically used in as a support material or for radiation detection. And the extrinsic is used in the day-to-day electronics, and also we can have a solar cell out of the silicon wafer, but of the lower purity. Sorry. So as you can see, there are, depending on the purity levels, in the previous lecture, Dr. Shashwati has already informed about the purity of 13N purity germanium. So depending on the purity of the silicon, there are different grades. So it starts from metallurgical grade, which is nothing but 98 to 99% purity silicon. And as we increase the purity of the silicon, the highest purity what we are targeting is detector grade, which is around 11N or 12N purity silicon. So in the worldwide, there are two major processes which are used currently for production of silicon The major use where the silicon is going right now are the two. One is for solar application and other is for semiconductor. So the process remains the same for production of both the silicon wafers for solar as well as semiconductor grade. Only thing is the purity level increases, the quality control of the semiconductor is on a higher side as compared to the solar cells, which what we are using. So the major process which is used worldwide is the Siemens process, which the major component or the chemical component which is used there is TCS, which is trichlorosilane. It is similar to it is SiHCl3 with 3 chlorine and 1 hydrogen. And the other is the union carbide process. This uses silane, SiH4. So this TCS has, you can produce polysilicon with all the 4 variants of this silane, replacing one H with Cl. So TCS, dichlorosilane, SPC and silane, all the 4 can be used. But the issue, depending on the efficiency of the process and the difficulty in handling the component, worldwide majorly people are using trichlorosilane as it is easier to handle and toxicity wise, and the energy component is also less as compared to STC. So I'll brief upon the chemical process. So the process starts from silica. So after carbon reduction of silica, we are getting silicon. This silicon is 98% pure, and we need to go up to 12N or 11N depending on the application. So we need to convert these solid particles into a chemical which can be used for using a chemical process. We can purify. So we have used trichlorosilane, which converting silicon with HCl, and we get a TCS plus hydrogen. This process is using a fluidized bed reactor, and after this we are getting a TCS which is as pure as the feed material, which is metallurgical grade silicon. So the impurities majorly consist of iron, aluminium, and calcium. So we need to remove that, and lower range we have impurities from phosphorus and boron and other metal chlorides. So all those things have to be removed from the TCS. So for that we are using purification step, which is distillation towers. So the distillation process, as TCS is has a boiling point at around 30 degrees centigrade at room pressure, atmospheric pressure. So this distillation is possible, and with the help of this series of distillation units, we are able to get a high purity TCS. Now the silicon is in chemical form. We need to again separate and get a silicon in the isolated elemental form. For that, we are using a polysilicon CVD reactor, and in this we can we will have a reactor which will be passing TCS along with hydrogen, and this reactor operates at around 1100 degrees centigrade. And selectively the silicon rods are only heated. This is the chemical vapor deposition reactor, where the deposition happens over the substrate. The substrate itself is silicon, so there is no chance of impurity from the environment where the reactor is operating. After getting this silicon, this is a polycrystalline silicon. So to use in semiconductor or solar application, you need to convert this polycrystalline to a monocrystalline silicon, and for that there are processes like crystal pulling, which is used. There are two type of crystal pullers in the market, two techniques. One is the float zone and other is the Choklavsky puller. So depending on the application, if you want a very high purity monosilicon, then you will be going for a float zone process. The limitation of the process is you will not be able to grow a very large crystal out of this, and the process is also manually controlled. It is not automatic. As compared to a CZ puller, where you can use a PLC based system to control the process, which is used in the solar application, as well as high purity magnetic CZ is used for semiconductor application. So these are the two types of pullers. So this is the magnetic CZ puller, and this is the float zone puller. I have listed on some of the differences between the two. So if because the CZ cooler uses a crucible, so crucible is of quartz. So the impurity from the quartz are also added to the this liquid solution of silicon. So that's why if you want to have a much more purer system, one has to go with the float zone. There is no contact between the melt and the support because it is a hanging process. That there is no support required in this float zone process. The growth rates of a float zone is comparatively higher than CZ, but the failure rates are higher in a float zone cooler. So this is the crucible where we keep silicon chunks, and these silicon chunks are melted, and then we incorporate a silicon seed. Depending on the orientation, what we want of the crystal, we'll introduce that seed, and then the pulling will happen upwards. So this is a process of the float zone. As you can see, there is no contact on the right hand side. So the crystal, the polycrystalline silicon is hanging from the top, and we introduce the silicon seed from the bottom, and then the pulling happens downwards, and only a small zone is melted, hence the name float zone. So it is floating, it is not contained inside any vessel. So there is no chance of impurities from vessel to the silicon melt. So after we get a silicon crystal, there are many mechanical operations that needs to be carried out before getting the wafer. So the ends of this silicon ingot is conical and has a large number of dislocations. So these ends are cut down, and the middle part is used for further processing. Because of the crystal growth, there are waviness in the crystal that needs to be removed to get a perfect diameter for processing, further processing. So then we go for a OD grinding the outer surface of the crystal. Then because there are different orientation possible in the same crystal, and each will be looking same, and the processing person will not be able to guess what processes to be used and how it is to be used because of the orientation. So we need to have a sign of a flat grinding. So there are semi guidelines for different orientation. You will be having different way to give notch or flat on the crystal, so that who's processing further will be able to know the orientation of the crystal. Then we'll get multiple wafers from this diamond cutter, and this wafer will be having some irregularities on the surface, which will be removed by doing lapping and polishing. And the final surface will be doing some characterization, lifetime, and getting the impurities in the using Hall effect, and then we will be able to certify this the wafer that are produced are reductive grade wafers. So this is the pictorial view. So these are the silicon chunks, polysilicon chunks that are fed to a puller, and then from the puller we'll be getting a monosilicon ingot. This ingot will be doing the slicing into wafers, and then it will be given to the fab. And fab will be further processing on these wafers to produce either semiconductors, chips, or use it as a substrate. So basically, the worldwide the concept of fabless company, silicon foundry. So all this has happened, evolved over the time. So what we have listened right now, the 3 fabs that will be inaugurated, mostly they will be as a pure play silicon foundry, where people will be sending their design to get it fabricated. The fab will have all the facilities from lithography machines to ion implanters and other characterization facilities also. So anybody who wants to use that use fab will have to have their own design, and they can send it to the fab, and the major concern is related to the IP, and the fab will be responsible for the IP production. So the major companies that you must have been listened to, like TSMC or Tower Semiconductor, those are pure play silicon foundries. And the fabless companies like Apple or Nvidia, they are holding the design part, and they are transferring the design part to the foundry where the actual fabrication of the ICs are happening. So I have listed on the specification of a detector grade silicon. So detector grade silicon has to have a very high resistivity with the starting criteria, then the carrier lifetime, and then we are controlling the donor or acceptor impurities, because each impurities will affect the performance of the detectors. Hence, the purity of the crystal has to be very pure to avoid any background disturbance due to any background during the detection. So these are the photodiodes that are being manufactured on a silicon wafer, and from this photodiodes, so after the fabric, this is done in a fab, and then afterwards it will be packaged into a detectors, and these detectors can be used for radiation application wherever required. And similarly, ICs are also manufactured on wafers and then packaged to different smaller products. So the working principle of silicon radiation detectors are like, there are two methods that can be used. One is directly a particle which can interact with the silicon wafer, can generate electron hole pair, and depending on the circuit, will be able to detect the radiation. The other is like, if the particle is not able to interact, you can have a secondary method, like you can have a scintillator mounted over the photodiodes, where the X-ray or the gamma ray interact with the scintillator, and the energy is then passed on to the silicon wafer, a silicon photodiode, which will again generate electron hole pair, and you will get the signal. This is just what is the status right now. So what you are seeing on the left is a distillation unit, PCS distillation unit. These are very large production plant, just like oil and gas. And on the right, what I have shown is who is having the major capacity. So because of the solar evolution during the last 10 years, the major capacity is available with China. There is few plants that are functional in Korea, Saudi, and Europe. The majority still lies with China. So because polysilicon is the raw material for monosilicon, so if you can correlate the same lies with the China. In Indian scenario, so before the 3 fabs that have been inaugurated right now by our esteemed PM, these are the 3 fabs that are available in India, and they are operating from the last many years. These are basically government owned fabs, and their main agenda was for defense application. So Sitar at Bangalore and Hyderabad, Bharat Electronics at Bangalore, and SCL in Chandigarh. These 3 are the major fabs that are working right now in India. And as I told you, these are only the fabs. Designer can be from any institutes or from DRC or from DRDO who can use these fabs. Going ahead, as you can see, this is the wafer capacity which is lying in the world. So this is the 2020 data by IC Insights. So the wafer capacity majority for different application, like depending on the nanometer. So you'll be listening to 6 nanometer, 7 nanometer processors from Apple. And what we're using in the home application is a larger nanometer application. So depending on those different applications, the capacities of wafer processing is available at different countries. It is definitely worth for India to venture into it because of the amount of the projected growth rate of this chips industry, and also to make India self-reliant. So we are almost using mobiles, laptops, and home automation. So all these things will be made in India, and it will be it will make India Atmanirbhar. Thank you.
Thank you, Dr. Subhadip. I have 1 or 2 questions. Any question from the audience?
Excuse me. How do you detect that defects level in less than parts per billion? Because when you are saying that the impurity level is less than 10 to the power 10. So how do you detect? And also, if you can detect, then there might be two types of defects. One is due to the presence of the foreign atoms, or the defects due to its crystalline structure. So how do you distinguish at that level?
So for the impurities related to the chemicals, so these chemicals impurities basically because of the process itself. So for production of polysilicon, if it is very high purity, then you will be getting a high purity polysilicon, and this will subsequently lead to high purity monosilicon. So depending based on FTIR, if the impurities of carbon and oxygen and in the crystal, or we can use the ICP-MS for detection in metallic impurities in the TCS itself, and neutron activation analysis also can be used. So depending on the different cases, we are using this, and the quality of the crystal we are judging by doing a Carrier lifetime. So if the Carrier lifetime is not up to mark, then we definitely know there is some problem in the crystal. We'll retrospect, go deeper into if it is due to impurities or if it is due to the structural defects.
Now, do you have any specific characterizing technique that you have that sensitivity of that level?
No, so we are using general chemical instruments. So apart from that, if you want to have a know about the electronic and magnetic properties, you can use Hall effect. Only by secondary method we are able to get the purity of the crystal.
Thank you, sir. So, on behalf of HBNI, I thank Sir Gupta for giving a beautiful talk on the silicon, its applications, especially the role of international community and the importance of our country to go ahead with this. So, thank you very much, sir. On behalf of HBNI, may I request Vice Chancellor to present a small memento to Dr. Slope. Thanks. We'll move to the next lecture. Will be on lecture 3, semiconductor processing using plasma and ion beam. The speaker of this session is Dr. Mukesh Ranjan, Scientific Officer G from Institute of Plasma Research. PPT.
I don't need PPT, sir. Mukesh.
Yeah, man.
Can I share my?
Yes. So Dr. Mukesh Ranjan is a scientific officer G and an associate professor of HBNI. He completes PhD in Dresden, Germany in 2011. Before that, he has completed his MTech and his MSc from IIT Kanpur and IIT Roorkee. He got DAE SSPS in the Achiever Award in 2015. Has had many innovative talks delivered and session chairs in national and international conferences. For his contribution, he already have 106 publications with an index of 25 and iron index of 50, and he has 63 proceedings papers, 4 book chapters, and 4 patents to his credit. Dr. Mukesh Ranjan has already completed 40 R&D projects, including bilateral projects for ISRO, DSC, DAE, and J&J, IITs, and many universities in CSR, etc. He has already guided for 5 PhD students, currently guiding 3 and several postdocs and master's stages. His research interests are in the fields of plasmonics, SERS, plasmodiagnetics, and sources, plasma material interactions, ion-induced surface monopatterning, surface readability, plasma-based technologies, and PVD film growth. So with this introduction, I request Dr. Mukesh Ranjan from IPR to deliver his talk on semiconductor processing using plasma and ion beam. Over to Dr. Mukesh Ranjan to IPR, please.
Thank you, Professor Salvin. Is my voice is audible?
Yes, sir. Yes, sir.
And my presentation is also visible?
One second. Then we'll ask you.
The screen has been shared.
Right. Is that visible, sir? Can go ahead,
Okay.
please.
Okay. Thank you. Thank you for the kind introduction, and I'm very much thankful for the HBNI for giving me this opportunity to talk about the
So this is
what we are
participant.
what we are doing at IPRs. There is a lot of opportunities available in plasma-based processing in semiconductor, and historically, actually, plasma has been used for various semiconductor processing, chip designing, fabrication, and so on. So I will be touching the what we are doing and what is the possibility can be actually in collaboration with IPR can be go ahead for if anybody has any requirement related with plasma-based processing. So in the morning session, we have heard about how we can actually, I'm very happy to see that already in BRC and other units, they are developing the wafers scale or the semiconductor scale. So we have a knowledge about that, how the single crystal germanium or silicon can be grown in the lab. So to step
Next
further,
one.
when you are making the ICs or the fabrications, you need to give some kind of fabrication, some kind of patterning on the surface. So what you see on the screen is just a memory device. What we are witnessing nowadays that every day the new mobile is coming with a faster memory storage. So the capacity of storage is increasing day by day. The laptop is in our PCs also. So what they're actually doing.
Slides are not moving, please.
I have changed the slide. I am on the second slide.
So,
should I try again?
Please reshare the slides, sir. Okay.
Just a minute.
It's still showing the first slide.
Is it visible now?
Reshare slides.
Reshare. Okay. So sharing entire screen. Share. Is my slide is visible?
No, sir, no, sir. Wait. I will take some time, sir.
I'm sharing the entire screen. Should I share only the presentation?
Only the presentation.
Normally, when we share the screen, it's easier. So that's why I tried it. Is it visible or not? I can give you another try.
Still, we could not see your slide.
Okay. So let me try again.
Please to reshare it.
So share.
Yes, sir.
Is it visible now?
First slide, yes.
And second? I have changed the second slide.
You can make it full screen, sir. No.
It is already full screen in my PC.
I think the log out and log in.
Robot. That you can tell him to log out and log in again. Log out and log in again.
Where?
Please ask him to log out.
Sir, you please go out and log out and then log in, then it will be easy.
You mean out of this
WebEx?
Yes, sir.
Yes, sir, I think. You can make the full screen. Sir. Already you have made the full screen?
So when I make it full screen, it
fine. Go to make it full screen.
I already did it the full screen. Is it not visible, the first slide?
Thank you.
Is it visible now? I can go in this manner also.
But then you just log out and then again log in. It will be easy, sir. Maybe some difficulty.
Okay.
You can tell him that you can share us the slide. I will share my screen. When he will be sent next, I will change this.
Hello. Hello.
Hi, sir. We could see your slide.
Now it is in the full.
Yes,
So now it is
yes.
in the full presentation mode.
Yes, sir. Good. Move to the next slide, sir.
I have moved. It's not moving. In my case, it is already changed. But do you see the second slide?
No, sir. Still we are seeing only the first slide. So you can share the full screen, sir, now.
I have shared the full screen only.
Yeah, if you have shared, share full screen. Make your PPT available in the desktop. Open. Yeah, now full screen is there.
Let us see if in this mode, can you see the second slide now?
Yeah, but
Yeah.
it may not be. So can you go to view? Please, can you go to view? You have not the last one view.
I have chosen the the full screen mode. So in my PC, it is visible.
Sir, it is okay, sir. Please, can you choose view? Click view.
I am in the presentation mode only. Slideshow.
Yes, sir. In the screen.
Please go ahead. Please go ahead.
I think if it is not very small, I can go ahead like this. Yeah.
No, you have to go to view mode and then click full screen. Can you go to view? I am asking.
So in the top view.
Click. And then now you will see full screen,
Full screen? A full screen option is there, na? On the bottom.
पीपीटी के ऊपर व्यू है ना, ऊपर जाने बोल रहा हूँ।
हाँ, तो अब क्या क्लिक करना है? Into window.
Maybe the reading view. There is a reading view that when you click 1, 2, 3, 4, 5 reading view. Yeah.
Is it visible?
Can you move
Second
down?
slide? Yes, and I'm on the second slide now.
Yeah.
Is it visible?
Go ahead.
Okay, thank you. Sorry for this interruption. Let me try one more slide. So this slide is also visible?
Yes, sir.
Okay, good. Fine.
Go ahead.
Okay, so now we can go ahead. So what I was talking about that since morning talks, we have heard about that how we can make single crystalline silicon and germanium semiconductors in the lab. To move forward, nowadays we need to pattern them for making different kind of applications. So what you see on the screen is a memory device. So nowadays the requirement of the memory device is also increasing day by day. So people are trying to make miniaturized magnets on the surface. So first case you can see in the bottom image, you can see the 50 nanometer scale, and the second one is a 500 nanometer scale. So in the same device, when you have to actually make a miniaturized small nanoscale magnets, you need to pattern your surface. So this is an example to increase the earlier what people were doing like in the CD drive. So they were making a coating of magnetic materials, and so it was randomly making the magnetic domains. So that was responsible for the memory recording. But with the help of technology advancement, now people are making small patterns on the surface, so that each individual pattern can behave like a individual magnet, and the data storage capacity is increasing. Similarly, in our touch screen, the sharpness of our screen is actually increasing. The resolution every time when we go to the market, they offer a brighter or a high resolution, clear displays. So there also what they are doing, the field effect transistor FET on the surface, they are actually making miniaturized. So day by day at the nanoscale dimension, they are actually going down and down. So pattern media has a lot of importance on so how to pattern a surface. This is another example where actually the data can be transferred very fastly in a processor. So nowadays we have a random access memory. So they take the data from the processor and then they send it to the they take it from the CPU and then they send it to the computer. So they use the copper wire. So instead of copper wire, if you have a pattern surface, you can actually transport the light, catching the signal. So in our optical fiber cables, the data is actually already transferred from one place to another place with the speed of light. But in actual circuits in between processor and the CPU, it is still some kind of wiring is used. So we can actually pattern our semiconductor, and then the light can manipulate from one direction to another, and it can collect the data. So this is another example here where the patterning is needed at a very narrow scale so that the data can be transferred. So there are two methods available. One is lithography. So like if the previous speaker was talking about, the focus ion beam is already there, and electron beam lithography is already there to make nanoscale features on the surface. But the problem is these kind of processes, they are highly precise, but they are very expensive, and and they're also very slow. So if you have to write some structure over the surface, the area they will choose in few microns, and the time consumed by them is very, very high. And in between, if the process is failure, the entire writing process will be destroyed. So as of now, I do not see that any of the Indian companies, they're actually making the lithography process. In coming year, I hope to get that even the Indian companies will also start making the lithography process. The another approach for patterning the surface is the self-organized way. So they are naturally the atoms can actually by adaptance and process, they can actually self-organize over the surface. So it has an advantage that normally most of the self-organized processes are very fast, and they can be implemented over a large area. But we need to optimize the requirement based whatever application we are looking. So top down and the bottom up approach both are going side by side, and in certain cases one has the advantage, and in another cases another has the advantage. So plasma-based processing, already you might have seen that plasma is a very good etcher. So plasma-based etching is normally used for cleaning the silicon wafers or any process whenever you are going to start. Normally the plasma-based etching is used to clean the surface. So commercially, plasma-based etching systems are available in the market, and many industries in India have seen that they already procure it. Institute for Plasma is also capable to offer this kind of plasma etching systems. Doping, we know that when we mix the material, like in semiconductor, we talk about p-type doping, n-type doping. So plasma-based implantation, plasma-based ion implantations are popularly used because normally not one cannot go to big implanter facility all the time. And the plasma-based implanter, they're actually very handy and then compact in the shape. So this plasma-based implantation are also used in the semiconductor industries for different kind of doping or the other requirements. So like people are making dilute semiconductors, magnets. So if semiconductor can also behave like a magnets, if you implant some magnetic material inside the material. So those kind of work people are doing using the plasma-based ion implantation. Surface nanostructuring, which is the topic which I'm going to cover in my talk. So as I said, that texturing is very important to make any kind of ICs and different kind of ICs. And so if you are making some magnetic device, if you are making some sensors, so some kind of patterning is always needed. So plasma-based nanostructuring is the topic which I'm going to cover. And then different kind of coatings are also used when you are fabricating. So different kind of layers are used. So plasma-based coaters are available in the market, which are used for making different kind of ICs. And in my talk, I will be also covering that self-cleaning surface is also one of the area which is very important. For example, if you have to clean your solar cells, there's a major issue that the dust is accumulated after a certain time, and when you wash it, the dust is stick there. And also in the electronic circuits, you do not want to have any dust accumulation, and so we need a waterproof electronics chips which is self-cleaning. So I will be touching these two topics in my presentation. So basically the content of my talk, I will be showing you how the plasma ions can be used for making a peri-pattern surface. In this case, I will be showing you the example of silicon. And this can be used for detecting the different kind of food adulterant. And we have actually developed, by making the patterning on the surface, we have finally developed a product which is commercially available nowadays for detecting different kind of food adulterants. And then I will be showing you how the surface can be patterned for the self-cleaning application. And in the final talk, I will be showing you that actually the plasma-based processing can be used for making small devices of micron size over the surface. So this is what you see in this picture is the silicon wafer. Complete wafer can be actually patterned and make small synaptic emulator devices. So just to start, I will briefly introduce you what is plasma. So as we already know that there are three states of matter: solid, liquid, and gas. And in this, all the three states, the atoms remain in the neutral form. And in the solid state, they are tightly bound. In the liquid state, they are a little bit flexible to move. And in the gaseous state, they are free to move, but still in the neutral form. So what happens when you give some energy to the outermost electron of the which is revolving around the nucleus? The electrons emitted from the atom, and then what remains is the what remains is the ionized atom. So if you keep on giving the energy, the electron will come out from the system, from the atom. So you will have a combination of electron as well as the ions and the neutrals, the gas neutral. So this all together, this combination of ions, electrons, and the neutrals is actually popularly known as the plasma state, and we call it as the fourth state of matter. There are many examples in real life which you can see about the plasma, like the sun is example of plasma which is continuously giving us the energy, in which our department is actually working on the fusion based energy. It's a futuristic project. Another example is the lightning in the rainy season. So a lot of charge accumulated in the cloud, and that try to discharge itself to find the nearest ground. In this process, they actually make the plasma which is of the neutral gas available in the atmosphere. So it's an example of atmospheric pressure plasma. So this lightning is an example of plasma. This the gift item which you see in the market is also an example of dielectric barrier discharge plasma. When you touch it, it makes a different short circuit and then spikes to make a short connection to the ground. The fourth one is the welding process. So all this kind of example you can see in your day-to-day life. And this is an example of the lab-like plasma, which is, we call it as a low temperature plasma. So typically those who have never seen the plasma can see, whenever you see a plasma, you will always see some characteristic color, because the electron get excited and then they de-excited and then they release some photons. So they get, depending on the type of gas or the kind of plasma you are making, it make different kind of colors. So just to show you how the DC plasma look like, for example, in the case of argon, it generates some pinkish color. Second example is the ion beam. You can see that wherever the beam is going from the ion source to the substrate, in this case, it is actually weakly ionizing the neutron molecules. So that color generated. The third example is the RF plasma etching. So this is what the process normally used in the semiconductor industry. So you can put any object inside the plasma, and then the plasma will homogeneously cover it, so that this is the beauty of the plasma, that whatever object goes inside, it covers it in the surrounding homogeneously. So whatever process you want to do, it actually just makes sure that it happen on the entire surface. So it's not a direction dependent process. The bottom plasma is example of tokamak plasma, and the plasma is also used as a plasma thrusters in the satellites. So how we make the patterns on the surface? So as I said, whenever we immerse some object inside the plasma, what will happen? So in this cartoon, you can see this is a typical example. So we have nearly equal number of ions and electrons. The pink ball is corresponding to the ions, and the sky blue color smaller ball is representation of electron. So when I run this animation, what you see that because electrons are much more mobile compared to the ions, so they immediately lose to the boundary. So whatever boundary, either your vacuum system or your substrate, electron will like to lose immediately, and following the electrons, ions will also go in the same direction. And if externally you are giving some potential to the substrate, the ions will hit the substrate. So this is a macroscopic picture. So you have electron and ions will hit the surface if you negatively bias the surface. What happened at an atomic scale? So if you see this in this movie, so the ions is hitting the surface. Initially, if you have a perfectly crystalline silicon wafer, so what will happen? It will in this process, it will remove some atom from the surface. So atom can leave the surface, and once the atom they get some energy from the incident atom, they are getting excited, and then they will try to neutralize this energy by walking over the surface. So there's a surface walk possible, there's an ejection of atoms possible, and then there's a possibility that ion can go deep inside and make the defect over the surface. So many processes happen when the energetic ions actually bombarding on the surface. So this animation is actually summarized in this picture. So what you see here is the energetic ions hitting the surface. You can see the sputtering process is happening. Some atoms are ejected. Some atoms can actually accumulate over the surface. Some can actually go and cluster formation happening on the surface. There's a defect formation on the surface. Some can also walk. So depending on the kind of ion you have chosen, the kind of material you have chosen, the kind of energy of incident ions you have chosen, the angle of incident, many processes happening over the surface. And using these parameters, you have to optimize your experiment to actually pattern your surface to make the self-organization. So what you see in this picture, normally if even you have a perfectly crystalline surface, the moment ion hit the surface, they makes it amorphous. The moment the surface is amorphous, it has some roughness. So even if I'm talking about the atomic scale roughness, normally people talk about the roughness in terms of micron, in terms of millimeter, in terms of nanoscale. What I'm talking about, even if you have an atomic scale roughness over the surface, so when the ions are hitting on the surface, they can, depending on the location or where they're hitting the ions, on the surface, the energy deposition will be different. So for example, when you see in this picture, the valley region, the energy deposition is actually higher compared to the hill region, and that makes your surface unstable. So once the surface is unstable, you have a more erosion at one place and less erosion at another place. So this makes faster erosion at one place, and so this finally land up in the making of this kind of wavy pattern on the surface. So there is well known theory which talks about the surface erosion and the surface diffusion process fight each other, so that you are landing in to make this kind of pattern on the surface. So if the ions hitting at a normal incidence, what you see the example on the left side is the gallium antimonide, which is also a very well known semiconductor used in solar industries and for various detectors. So when the ions are hitting at a normal incidence, they make this kind of dot structure over the surface. And if you see the bottom cross section image of cross section TEM image, the aspect ratio is very high. Typically, you can change it by changing the ion energy. I will show you the example. And on the right image, the middle image, you can see when the ions are hitting at an oblique incidence, they make this kind of wavy pattern on the surface. And the bottom is the cross-section TM image. This is an example of silicon wafer. So silicon 110, 100 or 111 show this kind of behavior. So this is a self-organized pattern formation on the surface. So we are just bombarding the surface at an optimized angle or optimized dose. And then it's by the self-organization process, which I explained earlier in my previous slide, they are making this kind of dot as well as the wavy pattern on the surface. And already this has been seen even in the theories. There's a very well-known theory of Bradley and Harper, that if you give the input of your experimental parameter and then add and then run this simulation, which has two components, one is surface erosion and thus one is surface diffusion, it also making this kind of pattern formation even in the simulations. So this kind of pattern formation, it's not very specific to only happen on the semiconductor surface. So people have reported this kind of pattern formation on different other materials. Like, so semiconductor is one example, metal is another example, dielectric mica is another example. So it's not specific to only semiconductor. This kind of pattern can be formed over the surface on semiconductor metal and insulators. And but for depending on the type of material you are choosing, you have to choose your the parameter of your incoming ions and the dose. Just to show that how precisely you can tune these patterns, I would like to see that the scale bar shown here is the 400 nanometer, and it's an image of 2 micron by 2 micron. And typically these are nano patterns having the wavelength in the range of 30 nanometer. So when you change the angle of incidence of your ion, you can see that the surface is changing. These are atomic force microscopy high resolution images. You can see as the angle of incidence is changing, the wavelength is increasing and decreasing, and the ordering of the ripple is also changing. And if you change the dose of your ions, initially you make a very shallow nano patterns of around 20 nanometer range, and as you increase the fluence falling on your sample, you can see that very nicely you can have a control of over the wavelength on the surface. So if I summarize this this AFM image in the form of a plot, you can see that as the fluence is changed, the wavelength is changing from let us say 20 nanometer to 40 nanometer. And if you change the incoming ion energy, instead of 500 dB, you can do it 300 dB. Then also you can change the wavelength of this pattern. So by changing the plasma parameter, the flux, the incoming ion energy, and the angle of incidence, you have a control of changing this kind of pattern formation over the surface. And recently, what we have seen that not only this kind of wavy nature of patterns are formed on the surface, you can also make a triangular type of structure over the surface, which are also form another form of self-organization. So when the silicon wafer is actually bombarded with 500 dB ions, they not only make a ripple pattern, but they also make this kind of triangular structure over the surface. We thoroughly did the experiments and then find out under what parametric window this kind of triangular pattern can be formed over the surface by changing the ion energy, by changing the fluences. And then we noticed that the dimension of this triangular structure is very much dependent on the experimental parameters. The d value is changing, the angle of the triangle inside is also changing. So depending on the parameter you choose, you can also pattern this triangular structure over the surface. This is another example where the plasma-based processing can be used for making dot structures. And we have developed a in-house plasma device where you just need simple permanent magnet and it makes the fireball plasma. So you can actually make this kind of dot structures by changing the ion energy. You can change the aspect ratios. So these are the TM images shown here. So initially when it is bombarded with 200 dB ions, you make very small and very closely sitting around 30 nanometer and 30 by 30 nanometer dot structures. As you increase the ion energy and keeping the fluence fixed, you can see the aspect ratio is changing. So by changing that simply by ion energy, you can actually tailor the aspect ratio of your nanodot structure over the silicon surface. So now I will show that I have shown you that using the ion beams or the plasma ions, you can make different kind of patterns which are self-organized in nature, and you can tune them in the nanoscale by simply changing the ion energy and angular incidence. Now I'm going to show you how you can use them for some certain sensing application. So once you have the pattern surface, either the dot structure or the ripple patterns, you can use them as a template. And then by using any PVD method, you can actually deposit the natural nanoparticles. So if you do not have a pattern surface, what will happen? This nanoparticle, they will start agglomerated over the surface, and the distribution of the nanoparticle will drastically change. You will have no control of interparticle gap. So if you have a pattern surface, because each the dot structure is actually very separated. So you can see in the SEM images that every dot has a single nanoparticle sitting on top of it. And on the right side, if you have a ripple pattern, you can see how nicely you can control the growth of the metal nanoparticle over this ripple pattern surface, and they make nice chains of ordered nanoparticle arrays. So once you have a very well organized arrays of metal nanoparticles or nanodot structures, they are very good, useful for the surface enhanced applications. So in my lab, we have tried different kind of dot structure of 30 nanometer gap, 50 nanometer gap, 70 nanometer gap, different type of nanoparticle arrays which are deposited over the pattern surfaces, 20 nanometer to 45 nanometer, and it can go up to hundreds of nanometers. We can also make the nanowires. The nanowires has application in transparent conductive electrodes. So if you pattern your surface and deposit this silver nanowires, they will have a conduction as well as the transparency. So touch screens are now used either graphene or silver nanowires for these applications. So with this, I will now show you how the patterns, this kind of ordered nanoparticle arrays can be used for a very good sensing detectors with the help of surface enhanced Raman spectroscopy. So briefly introducing you what is surface enhanced Raman spectroscopy. So typically, if you want to detect a molecule with the help of Raman spectra, I'm going to show you the example of 10 to the power minus 6 molar concentrated rhodamine 6G molecule. And what you see in the first plot is that you do not see any characteristic peak of the molecule, which normally should be seen in the Raman spectra. And we only see a very fluorescent band coming out there. And the intensity of the spectra is also very low. But if you take a drop of this same solution and put it on the metal nanoparticles, in this case, example, I'm showing you the randomly distributed nanoparticle as shown in these SEM images. So you see the characteristic vibration modes of the molecule which you want to probe. So these are very well reported rhodamine 6G spectra available in the literature, and you can see the intensity also increases drastically. So this is the beauty of surface enhanced Raman spectroscopy, because it increases the scattering cross section of the light interaction in presence of metal nanoparticle. So you get the higher excitation. So what is the key of this method is that the metal nanoparticles should be very close to each other. So when they are very close, typically less than 5 nanometer, the field enhancement between them is very high. Field enhancement is typically proportional to e to the power 4. This E is the electric field of incident light. Okay, so if E is the electric field of incident light, it will become 4 times to the power 4 high in between the metal nanoparticles. So we need to put our molecules somewhere in between these two nanoparticles so that you get the high sensitivity in the Raman signal. So why we are interested to detect the molecules? I introduced you that surface enhancers can be used for detecting the molecule, but what is the need? Nowadays, food products have different kind of adulterant are used left and right in the market to make them very beautiful, make them very juicy, make them very tasty. Different kind of non-recommended dyes are used in the market. So whenever you go to the market, you will see, oh, this particular fruit is very shiny, very attractive, and then you immediately buy it. Okay, and these are some typical examples, but if you Google it, you will find many kind of food adulterant are used for different vegetables. So we want to detect this food adulterant with the help of surface enhanced Raman spectroscopy. Why surface enhanced Raman spectroscopy? Because in most of the cases, it's very difficult to detect the normal Raman spectroscopy because they're not sensitive to the Raman signal. So you need to have a collaboration with molecule and the nanoparticle to detect these signal. Another example is the use of pesticides. So those who are actually spreading the pesticide, they don't know that it is actually harming their own health. And there are several reports available in the newspaper that the honeybee dies when they consume the pesticide is spread over the leaves. Many peacocks dies, many birds dies when they consume this kind of dangerous pesticide. And when you are buying the product from the market, you don't know that actually some pesticide is still there on the surface after washing. So it's another issue which has to be actually taken care of. So what we have done in our lab that I have already shown you that we can make different kind of arrays of metal nanoparticles, and by optimizing our ion beam parameter and our growth parameter, we can nicely make chains of nanoparticles. So some example I have shown that over a period of time we did a systematic R&D on this topic, and then we found that somehow the 400 electron volt or the 500 electron volt patterns are very good because they are capable to make highly distributed, very homogeneous distribution of metal nanoparticle arrays. So they look like a perfect matrix. So if you put a molecular dot anywhere on the sample, you will see isotropic signal nearly at the same place. So with the help of this metal nanoparticle, we could able to detect the ppm level of pesticide. So normally you cannot detect this pesticide dichlorovirus with the help of Raman spectroscopy, but with the help of these metal nanoparticle arrays which are deposited on the pattern surfaces, you can actually able to detect them very nicely at 2 ppm level. Another example I've shown here are the turmeric puddle. So in turmeric, we see the yellow dye is added, which is methyl yellow, which is not recommended. And today only I was seeing, there was a news in Times of India that this normally children eat this gudiya ke bal. So they are using the rhodamine B dye in that to make it pink color, but actually it is carcinogenic. So they were using it without actually noticing that it can be very harmful for the kids. So those kind of dyes can be easily detected with the kind of sensor we have developed here. So the another example is the turmeric powder, and the chili powder has a red dye, and this watermelon juice has a azithromycin B dye which is used, and in the milk melamine is used. So different kind of food adulterant can be detected up to a very low concentration level with the help of the developed SCRS sensor on silicon wafer. Another example is the wax is used. So when we go to the market, we see that the apples are actually shiny. So they use non-recommended wax over the surface, which can also be detected. So you just have to wash all this and dip and take the water from the apple, and then when you take the Raman signal of this water taken from the fruits or the vegetable, you can immediately see the characteristic peak of the dyes or the food adulterant used inside the food product. We are also using this kind of nanopattern based sensor in collaboration with Tata Memorial Hospital for the earlier detections of the diseases. So what you see in this right side spectra is the Raman spectra of the MCF7 breast cancer lines. So if you do not have a nanoparticles, you will see a very low signal, or you need many number of cells to detect the cancer cells. But if you have a metal nanoparticle, you can very well resolve them very nicely, and only 1 or 2 cells is just needed just to compare the healthy cell and the cancerous cell. So this is the final picture of the we have filed an Indian patent on this. So what is there? This is a pre-patent pre-patent silicon surface deposited by silver nanoparticles, and it is highly sensitive surface enhanced sensor for detecting different kind of food additivants. We have commercialized this product, and technology agreement is signed with 2 companies. So it's available whosoever want it and want to test for different some drug industries, they are actually looking at it because every day they are detecting some new molecules for their study. So it's a very useful tool which can be explored for different molecular studies. I will skip this slide. So commercially, if you see the picture, there are many companies internationally selling this surface enhanced based sensors, like Ocean Optics is a very well-known company, Nanova USA, Americo Scientific, Himasu Japan. And in this case, if you need the surface enhanced substrate, the cost is very high, and you can only buy few of them. But now IPR based, this pattern is actually, it's very cost effective and it's very easily accessible. So anybody need, he can contact me. Now, with this part, I will now move to the surface compatibility. As I said, that we also need to clean the surfaces like the solar panels or the electronic devices. So how to make surface self-clean? So I'm going to show you a polymer example, a Teflon. Teflon is very well common polymer used for either in our lab or in different medical devices. So normally Teflon is already hydrophobic in nature, but the water droplet stick to the surface, it's not rolling down. Okay, so if you bombard this Teflon surface with energetic ions, or you keep it inside the RF plasma by doing some plasma etching, you can see that the contact angle is changing from 105 to 157 or 100 and around 60, and you make this kind of nanostructure over the surface. So what you see in the bottom SEM images that this is an example of 800 eV argon ion bombarded on a surface at 20 degree for 5 minutes. You can make this kind of micron size as well as the nano size structure formation on the surface. And not only the bulk Teflon actually show this kind of behavior, you can make a Teflon film and then pattern it. That also show the angle change after the ion irradiation. So both the film as well as the bulk Teflon can be converted to make self-organized nanostructure on the surface, which are super hydrophobic in nature. I'm going to show you one movie just to show what I'm telling. So this is an example of 800 eV, 180 seconds normal incidence bombardment of ions. You can see that
we are running short of time.
Yes, sir. This is. I will skip after this. Yeah. So this is an example that how you can make the surface. And even if you are pushing it, it is not sticking to the surface. So this is the beauty that how you can make very nicely arrange wettability surfaces. So with this, I will now go to my last slide, where actually wafer scale patterning is also possible in the lab. So these are some example of making synaptic emulator. We have successfully make different kind of small size devices and then actually shown their performance by applying different voltages and time scale, and actually show that wafer scale patterning is also possible with the help of plasma processing. With this, I will conclude that we are very open for any kind of plasma-based collaboration. So we can offer plasma-based etchers in our institute. We can help for plasma-based ion implantation. We can also help to make different kind of coating on the surfaces, and several other characterization facilities available at Institute for Plasma Research. Thank you very much for your attention. This is an example that how beautifully we have controlled the droplets over the surface by patterning them. And this is an example that these are two flowers in our institute, but the nature has filled the same dye in these two same flower. So the Raman spectra is showing the same peaks. These are my team which are working with me for making patterns, for making nanoparticle growth and working on sensor applications. Thank you.
Usage of plasma. We covered almost the plasma interaction, some animation, plasma animation, the ion interactions, cell population patterns in non-ion samples, change in patterns, and he has beautifully explained how these SIRS, surface area Raman spectrums, will be highly useful for even food product adaptation and this nano-level pesticide reduction. It's really an eye-opener for all the people how this basic technique of SERS is really useful in detecting all these things. So thank you very much, Dr. Ranchan, for delivering an excellent talk and topic about the SERS and its applications and where IBM is really involved in the research being used for the social applications. Thank you very much, sir. I thank Minor Brodovatiya, Dean Academics, for arranging in a short duration, very short duration, within yesterday, they have made all these possible. So I thank Director IPR for giving necessary permission to Dr. Mahesh Sanjay also deliver this talk. We will switch over to the next lecture, please. Thank you, Dr. Mahesh. Lecture sign off. We will go to the next lecture, lecture 4, by Dr. Tarun Kumar Sharma. It's also going to be another online talk. The application of phone semiconductor chips for lasers and detectors. Dr. Tarun Kumar Sharma is heading the Material Science section of Raja Ramana Center for Advanced Technology, Indore. Dr. Sharma also holds a position of trouser in HBNI, Mumbai. He joined RRCAT in 1995 from the 38th batch of BA Training School. He received Cohen Medal for standing first in the 38th batch of BA Training School, Mumbai. Dr. Sharma is the founder of Semiconductor Research and Device Fabrication Activity at Indore and is one of the most experienced accredited growers in India. He has worked at several prestigious institutions in India and abroad, like TAFR Mumbai, FBA Berlin, Germany, University of Surrey, UK, and Carnegie Mellon University, USA. Professor Sharma received University Merit Certificate of Meerut University, Meerut, for holding first rank in MSc. He is a recipient of Ireland Best Thesis Award for the year 2002, UK India Education and Research Institute Fellowship of British Council for the year 2007, and the Silver Medal of MRSI for the year 2016. He is also a recipient of prestigious Holy Science and Technology Award for the year 2011. Professor Sharma has guided several PhD and MTech students and has published nearly 350 research papers in peer-reviewed journals and conferences and holds an US patent also. So I welcome Dr. Sharma, Dr. Tarun Kumar Sharma, and the HBNI for delivering this talk. Over to Dr. Sharma, please.
Thank you. Can you hear?
Yes, sir. Yes, sir. Get chat.
There is a lot of why? Okay. Let's see how to. This is already unmuted. Can you hear me? There is a lot of.
Yes, sir. There is some kind of echo is coming. If you have.
Yes, that's what
I think you are joined with two network. Switch off one.
Log out. Log out. Okay. That is. Just log out कर दीजिए बस. Hello. Hello.
Yes,
can
sir.
you hear me now?
Yes, sir. We can hear you. Try to share your slides.
But we can't hear you. That is a problem. They can hear me, but now we can't hear you.
Actually, audio वहाँ से लगा हुआ है.
नहीं actually क्या हुआ सर वैसे नहीं. Hello, can you hear me now?
Yes, sir. Yes, sir. We can hear you. You are audible. You are audible. We can hear you.
Your audio is unmuted, no?
Yeah.
इसका ले नहीं रहा ना. इसका audio
सर वो
audio निकालिए नीचे से.
इसको लगाएं? हाँ लगाइए सर. Hello.
बट आवाज तो जा रहा था पहले. वो हो रहा था वो आवाज उसका भी ले रहा था पीसी वाला.
Hello, can you hear me now?
Yes, sir. We can hear you.
Hello.
You are audible. You are audible.
Can you hear me?
So just tap one more.
Yes, sir. You are audible. Go ahead, please.
Hello. नहीं.
Yes, sir, you are audible. Please go ahead.
Hello.
So
Just
can
keep
you hear
speaking.
me? Yes, sir.
Hello, can you hear me?
Yes, sir, you are audible.
But we can't hear them. That is a. So what do
Sir, you are audible. Please go
should I
ahead.
go out and come back again? Or I don't know. Hello. Hello.
No, sir. I am muted.
Pandita ji.
Yes, sir.
Hello. Are you
You
able
are
to hear
audible.
us?
Yes, sir, you are audible.
क्या किया जाए? इसका ऑडियो यूज करें क्या?
एक चीज ये कर सकते हैं.
इसका ऑडियो यूज करें क्या?
हाँ,
That we can do. उसको चलाओ. Okay. इसको उसी में लगा दिए नीचे.
उसको जहाँ लगा था
You are.
ऑलरेडी लगा हुआ है क्या? उसी को चलाइए. तो इसको
Sir, you can start. Your presentation. Start now.
Hello. Hello.
Ma'am, you speak.
Huh?
Now speak, ma'am.
Hello. Hello, can you hear us? Anybody from the audience? Can you confirm that?
I can hear your voice, madam, but not
can you hear me?
Tarun Sharma.
ये उसको म्यूट करिए. हेलो.
Please come forward. Hello.
Hello.
नो नो इट्स
चाहिए आप लोग क्योंकि यहाँ का वालूम इको कराएगा.
इट्स ओके.
आपके उससे जाएगी.
हेलो. Can you hear me now?
Yeah, you can hear you.
Can you hear me now?
But there is an echo.
But I cannot hear them. No problem. That is the problem.
Hello, sir. Some issue will be there from your side. You can check your audio section, or you have connected to the multiple device. Can you check once again?
Hello.
Because voice input and output is going properly.
Hello. Now is that clear?
Yes, sir. We can hear you.
Hello, we can hear you.
Okay. So let me share.
Please share the slide and start your presentation.
Hello.
ये स्क्रीन क्यों नहीं शेयर हो रहा है?
वो भी नहीं लगा. ऑलरेडी लगा हुआ है.
Hello, sir.
चलो ये
ऑडियो उससे ले रहे हैं.
ले क्यों नहीं रहे हैं?
उधर जाने के. उधर तो इससे ले. अपना देख लीजिए.
शेयर क्यों नहीं हो रहा?
ये problems in slide.
ऑडियो तो वैसे ही आ रहा है.
शेयर क्यों नहीं हो रहे हैं? स्क्रीन
जो शेयर हो संतोष आगे आया क्या? No. Yes, can you see my slides?
Yeah, you can see. You can.
Okay, and just go to view. View, reading view. So it's visible to you now?
You can just go down and see the next step. You can see the this side now. Okay.
Hello, can you see my slide?
Yeah. You can see the
And
slide.
it's moving also?
Yeah. Yes, yes, it's moving.
Okay, so let's go ahead. So I think ये यहाँ का voice बंद कर दीजिए. Okay, first of all, let me thank HBNI RRCAT, HBNI Mumbai and RRCAT for giving me this opportunity to showcase the compound semiconductor chips that we have been making in our lab during last 2.5 decades. And as you saw today morning that we had a grand opening or laying of foundation stone by Honorable Prime Minister Sri Narendra Modi for 3 fabs in India. And you all know that those are mainly silicon fabs. So why we the compound semiconductor people are keen about it or excited about it? It's very clear to all of us in R&D or in academia that whatever you do in lab, unless it goes to land or it goes to some application in real world, there is no real satisfaction. So you want that the R&D, whatever you do in lab, should go to some applications, but in semiconductors, it's not that simple. So actually, the route is something like that. That from lab you go to a fab, and then from fab, where is my pointer? So from lab to fab, and then it goes to real users. So ideally, there is no direct transfer of semiconductor chips from a lab to real users. It's always a fab, but there was no fab in country. And as was discussed in earlier talks, that we were talking for last 60 years and 62 years, and finally it happened. And it mainly happened because due to COVID, there was a strong shortage of semiconductor chips, and there was a worldwide push that you need China plus one. So you need semiconductor fabrication everywhere. So our country also picked up, and in 2022, India Semiconductor Mission was launched to create an ecosystem for semiconductor manufacturing. So although these fabs are mainly for silicon, so what is there for us? So in academia or in R&D, when you do research, publish or patent, and ultimately you want the technology to transfer to industry, but there was no fab as of now. So fortunately for silicon people, it has started today. So maybe in next 5 years, they will be able to transfer some of their technology to some of the fab, or maybe when these fabs are starting making devices, they will have some problems, they will face some challenges, and probably they will come to researchers that can you solve it. So we could be the solution provider for the fab. And especially for HBNI, this is an excellent news because our students will get jobs. So for example, whatever students, graduate from our labs, they get very nice postdocs in Europe or in US or in Japan or Korea. But when they want to come back, there are very less opening. They are mostly in academia. They are very limited. So once we have these fabs, so there will be a lot of opportunities for our students. So that is a really good news, and we are really excited about it. So here is a brief outline for my talk. So I will be presenting compound semiconductor chips for lasers and detectors, and I will be confining for the chips which we are making in our lab in RRCAT during last 2.5 decades. First, I will make a brief comparison between conventional or compound semiconductors, and then I will go to semiconductor laser chips, mainly based on gallium arsenide, which are mainly quantum well lasers. Then I will go to semiconductor detector chips, which are based on gallium arsenide and gallium nitride. we have tested them for their radiation hardness. I will present some data on that, and then I will present some data on chips for radiation detection, mainly for X-ray and gamma rays. And finally, if I have time, then I will come to spin optronic chips, where we detect spin and charge simultaneously. And these are some images from our lab where those chips we have been made in our lab, and I will be showing some of them in my talk. So let me come to the introduction to chips. You have seen some pictures. There are the pictures from internet I have taken. So in mostly the chips are based on silicon or germanium. They are conventional elemental semiconductors. So what you have a bulk crystal, and or you have bulk wafer, which could be about a foot big in diameter, and wafer could be like 500 micron, 3 micron thick. So this is like maybe P type or N type wafer. In order to make PN junctions, as in the first talk the speaker has mentioned, you put, like, let's say beryllium or lithium, either it's implantation or diffusion, you make PN junctions. And then once you make PN junction, you have to address them, you have to make contacts, so you do metallization. But you want to have multiple transistors on the same chip, so you have to isolate those transistors also. You have to do some isolation. So basically you deposit dielectric. And for making transistors, you want to make them as small as possible, maybe like 3 or 5 nanometers in size. So you have to do photolithography, and then you have to address them by using wire or die bonding or flip chip bonding. And you have to apply bias. You apply voltage, so controlling, and then you have to read out. So basically readout circuitry, and then packaging. So all these steps, they are essential for any semiconductor chips. So let it be conventional or compound semiconductor, those steps are common. So we also do most of them in our lab. So this is a simple example. In reality, the silicon chips are much more complicated. Say CMOS inverter. So you can see, like, there is N type substrate, and then you implant in some pockets and make them N plus or P plus regions, and then you make PMOS or NMOS. So essentially, or for making for isolation, you deposit oxides, or you make gate oxides for controlling them. But essentially, the heart of the device is a single semiconductor. And you make only N type or P type, but the main skeleton remains same. It's the same semiconductor related with silicon or germanium. And so it's a bulk growth. So there is no layer growth of semiconductor. So there is no epitaxy. In compound semiconductors, we do epitaxy. I will tell you in the next slides. And then we make heterostructures and quantum wells. So there is a brief comparison between compound semiconductor and conventional semiconductors. So let's say silicon or germanium. They are indirect bandgap materials. They are not good for light emitters or making lasers. The compound semiconductor, for example, like gallium arsenide or gallium nitride, they are direct bandgap materials. So when an electron recombines from conduction band to valence band, you can make light emitters or lasers out of that. They have different band structure or crystal structure with respect to conventional semiconductors. And because, let's say, gallium arsenide has 1.4 eV, gallium nitride has 3.4 eV, or we are making nowadays aluminum nitride is 6.2 eV. So we can make a lot of bandgap variation. So we can make heterostructures, and then by using heterostructure we can make quantum well, wire, or dots, which we are using in lasers basically. And essentially you grow layer by layer. As you can see in the bottom right hand side, you take a gallium arsenide wafer, then you grow aluminum gallium arsenide or gallium arsenide, and you make multi layers by using epitaxy system. The three epitaxy systems which are shown in this picture, they are in our lab. They are used for growth of gallium nitride and gallium arsenide based structures. So we can grow ultra thin layers, maybe about a monolayer thick. They are single crystal nature, and we can make atomically flat interfaces, which are essential for making quantum wells or quantum dots basically. So let me come back to semiconductor laser chips, which are essentially quantum well lasers. So for any laser, you need three basic ingredient. You need a gain medium, you need a cavity, mainly a resonator, and then you need a pumping mechanism. In case of semiconductor lasers or semiconductor laser chip, the gain medium is basically PN junction. You forward bias the PN junction, inject electron hole pairs, then they recombine near the junction and then give light if it is a radiative recombination, which happens in case of compound semiconductors, let's say gallium arsenide. But here there is a problem, because when you push electrons from p side to n side, or holes from holes from p to n side, electron from n to p side, they will simply diffuse to the other side. So the efficiency of these devices, they were demonstrated long back in 60s. It was very little, and so the idea was given here that you make a heterostructure where you sandwich a narrow band gap material, let's say gallium arsenide, between two wider band gap materials. So here electrons are confined to the conduction band, and holes are confined in the valence band. So both carriers are confined. And not only that, because of this band structure discontinuity, you have a discontinuity in the refractive index also. So your photon mode also is confined. So this was a Nobel Prize winning idea, which was given in 2000. Nobel Prize given in 2000. All the devices were demonstrated in 1968 or 70s. So, but there is a problem in this design, that because the central part, which is the active region, is only 0.2 micron thick, but laser could be like about a micron in wavelength. So the confinement of photons is not good. So in order to solve that, you have you insert two more layers, which are called wideband waveguide layer. So that waveguide is basically to confine the photons. So now carriers are confined to the active region, which is very thin, and then you have another heterostructure which is used to confine photons. So we call it separate confinement heterostructure, and we made some layers using this concept in 1999, and I am showing a view graph from this paper. So you can see the power was around 30 milliwatt. And this was the first time that such lasers were made in India at that time. I was a TFR at that time. So these lasers were made in Indian in that time, basically. Later, we set it up the same facility or a better facility at RRCAT. You can see there is MOCVD, which is used for the growth of quantum well structures. Then there are clean rooms for that. And here I am showing the power output of the laser. So it was around 5 watt, which we achieved around 2006. And then you can see like we involve different quantum wells. Let's say for 750 it was gallium arsenide phosphide quantum well. For 800 around it was gallium arsenide quantum well, or for 950 around it was indium gallium arsenide quantum well. So by choosing either the composition or the thickness of the quantum well, we could change the wavelength of the quantum well emitter. And it was in 2007 that we made indium gallium phosphide red lasers based on in-gap quantum wells, basically. So incidentally, we have a very wide wavelength coverage that we have made in our lab, and we are only lab in country which has such capability to produce laser quantum lasers over a wide wavelength range. There are other labs like SSPL Delhi or Siri Plani, but they have only availability on around 800 or around 980. So we have a wide coverage. That is the strength of our lab, basically. Then we try to enhance the power. So we could enhance up to around 25 watt pulse power or 3 watt CW power. And we saw that when we were ramping up the power, so the wavelength was shifting by around 4 nanometer from 2 to 20 watt. And this was the reason, because when we were trying to inject more current to get more power, we were not able to remove heat from the laser diode, basically. So heat was a major issue. So later, then we have gone to different geometries. So you can see like this is a side view, this is a top view, and the laser bar sits over here. And by using this geometry, we could demonstrate we use this device in this geometry. So there were 3 laser rods, and it was ND YAG rod sitting at the center. So we pumped the ND YAG rod by this, and then we could achieve 51 watt CW for ND YAG at 1064 nanometer, and 25 kilowatt pulse power from diode pump solicited laser, where lasers were bonded by our lab. So this was 2 years ago. Essentially, for a semiconductor laser, for a single emitter, it's a small chip. So length could be around 1 millimeter, width is around 500 micron, and the thickness could be around 100 microns. So it's a very small chip, like all dimension less than 1 millimeter. For example, you can see we have recently bonded a chip. It was bonded in last week only. So in a 1 centimeter long bar, there are 19. So each yellow region is a laser bar. Basically, 19 lasers are on this laser bar. It is sitting here, and then you can see the wires are bonded to address each layer simultaneously. So now we are going to couple this to a fiber. So this is very recently, but it's a, you know, the chip fabrication is very complicated, and it can be divided into three major parts. The first one is the growth of epitaxial structure, which is a multi-layer structure. So for example, here you can see there are 5 to 7 layers, but in reality there are around 30 layers in the structure. Each layer has a like different doping or different composition, different thickness. They have their own role. So then the next step is you have to make laser bars, something like that. So this is, as I mentioned in the previous slide, there are like 10 emitter or 20 emitter and in a 1 centimeter long bar. So, and then you have to bond this bar to make the laser bar, laser diode basically. So epitaxial growth, fabrication of the laser bar, and the packaging or bonding of laser bar for heat removal. So there are three parts, and you can pick up any parts, you know, nowadays. That is the scenario. And this part is the least cost intensive because you want to transfer the technology to some industry which is not available in the country right now. Hopefully maybe 5 years later we will have some industry in semiconductor, in compound semiconductors also. So we have made this technology for the bonding and packaging on the BRC website, and now 2 companies are contacting us to get the technology. So hopefully part 3 we will be able to transfer in recent future. And once that is successful, probably will, you know, encourage them, or maybe some other industry will come which can take part 1 and part 2 also from our lab. So this is the scenario on laser diode. Now let me come to photo detector chips, mainly based on gallium arsenide and gallium nitride. So we have made a lot of PIN gallium arsenide based detectors. You can see there are many of them made here, and then they work in the range of 400 to 850 nanometer. This is the band gap of gallium arsenide to decide the wavelength region. And then some of these detector we have put in an early arc detection system, which was installed in a RF circulator at RRCAT. So actually it acts like a safety switch. Whenever there is a arcing in RF circulator, it will give an alarm and it will switch off the RF circulator basically. So it was deployed in real applications. Then we made a different chip where 2 detectors were made on the same chip. So you can see there are 2 detectors of rectangular size, and it was necessary to record a elliptical beam shape of a laser, and there were 2 beams coming nearby. So the separation was decided by as per the requirement of the user. Such valence detectors are already available, but they are kept at a distance, as you can see the bottom part, and they are 2 different detectors, whereas in our case there are 2 detectors made on the same chip. So there are identical detectors. So it was necessary for the application. And then we have made a quadrant detector also, where we can have 4 detectors for using that can be used for laser positioning or of the beam basically. Now we are trying to make linear arrays or pixel detectors in our lab. So radiation hardness of detector chip is shown here. So we expose our devices to gamma radiation, and so you can see the black is the unirradiated device, and when we are putting more dose, the dark current was increasing, so it was showing some damage. So then we plot the current per unit. The dark current is a function of radiation dose, and the slope shows the degradation of the device basically. So lower is the slope, better is the device. So ours was 10 to minus 19. So if you take for silicon, it was 10 to minus 17. So it was about 2 order better than silicon. Then we try to compare gallium nitride devices also that we have made in our lab. So this is gallium arsenide device on the left. On right, you have gallium nitride based devices. So if you compare the dark current ratio between pristine and irradiated devices at minus 2 volt, it was 110 in case of gallium arsenide, and in gallium nitride was 3. So gallium nitride device around 50 times better than gallium arsenide device. So they are more radiation hard. So it was both devices were exposed to the same radiation. Then if we expose them to radiation, what do they recover? So it's shown in this device that the gallium nitride device recovers within a day, so without doing anything. So for example, for gallium arsenide device they take about a week, but gallium nitride device could recover within a day. So they are really radiation hard, and they can be used in a radiation environment basically. Then we have made some more devices where we are in this slide I am showing you the D star or the detective of the detectors as a function of some parameter. And in this plot on the right hand side, I am showing our value, which was as compared to the values reported by other researchers from the similar device. So state of performance of the device of this gallium nitride based chip was demonstrated by us in 2019. And then after that, we have made very special chip which was operating at the same wavelength like previous device, which was operating over a broad wavelength range. This was a very special chip. Detector chip was working at 360 nanometer, and it was able to detect within a window of only 5 nanometers. So a very specialized detector which have very wide applications in gas sensing, gas sensing. Basically, this was demonstrated us by 2 years ago. Then the same device, gallium arsenide based detector PIN device, we have exposed to gallium arsenide. We have exposed X-ray detectors. So you are seeing here that gallium arsenide detector is exposed to X-ray power, and so when we were increasing X-ray power, the response was rising, so it was responding to X-ray beam. Then we took the detector to Indus beam line, so you could see that spectral range of gallium arsenide based devices. So blue is gallium arsenide, and red is silicon. So you can see the silicon dies after 10 keV. All in comparison to that, our devices were working up to 20 keV. So 20 to 30 keV range they could cover. And in fact, then we used the same device to detect K edges of different elements on BL16 beamline of Indus 2. So we could detect those elements. It was in an X-ray fluorescence setup. So this was another application of the detector developed by us. Then we coupled our detectors to a cesium iodide tellurium scintillator, which was obtained from BRC, and we could detect gamma radiation by using our own detectors. So here you can see like we are plotting reverse bias, the response of our device is function of reverse bias. So it was responding, and this was another proof of concept demonstration that our devices could detect gamma radiation also. Finally, let me come back to spin optometer chips. I have few minutes left. So this device it works on a concept called inverse spin Hall effect, and it has two domains. One is gallium indium phosphide semiconductor, which is used for its specialized band structure, because using circularly polarized light, you can inject spin polarized carriers in indium phosphide, either spin up or spin down, and then we coat gold on top of that. And gold is used because of its spin is large spin Hall conductivity, where you can separate spin up and spin down carrier laterally. So once you inject spin polarized carriers in indium phosphide, you could separate them in the gold layer, and you can get a voltage. Basically, that is a concept. So on the right hand side, you can see like we are varying the degree of circular polarization from linear to circular and then to linear. So from right to left circular, and you can see the device is responding to the degree of circular polarization or spin state of the electrons basically. But there was a problem in this device, that the device response was also depending on the intensity of the laser beam. So there was a doubt whether the signal is because of the intensity or the spin state of the carriers basically. So then we discussed, I was discussing with Shailesh Khamari, who was working on this problem as part of his PhD. So he came up with an idea that now we can make two chips on the same device. So the left hand side part was the inverse spin Hall based device, which was detecting spin, which between 1 and 2 terminals, but between 2 and 3 was without any gold. So it was working like photovoltaic, like a solar cell basically. So that was detecting the intensity of the laser. So now you can see on the middle view graph that between 1 and 2, we are when we are changing the spin state of the carrier, the response is rising the blue curve basically. Whereas 2 and 3, which is the PV photovoltaic, that sense the intensity, there was no signal in that. In the last graph, you can see between 2 and 3, the PV, when we are enhancing the intensity, the signal between 2 and 3 was rising, whereas the spin part between 1 and 2 was constant basically. So there is no crosstalk between the two detectors. So we have two detectors on the same chip. One is sensing spin, other is changing basically charge or the intensity of the laser beam. So this was, and there was no crosstalk, and the device works at room temperature. In fact, this is a very frontline research group, and there are only few groups working worldwide in this area. Finally, I will take this slide. So we have in this slide you can see like because for inverse spin Hall effect you were using indium phosphide, and then there was a metal uh, for the separation of carriers. So there was a metal to semiconductor interface which kills spin polarization basically. So ideally if you can do all semiconductor device, then that was better. So we made all semiconductor device and we use electric field to separate the carriers, and injection of hot carriers for enhancing the device. So by using a 2, we could get 2 orders larger signal with respect to what we were getting earlier. So this was a all semiconductor device which was working at low bias. So low joule heating was minimized. We got high signal strength, and we have then performed a lot of time evolved studies or involve higher values. They are all in the publication, but I don't have time to go through all that. But this really, very frontline research work where we are working on spin polarized carrier injection and making chips for detecting spin and charge simultaneously. So finally, let me summarize. So I have given you a brief introduction of conventional compound semiconductor chips. We are making compound semiconductor chips in our lab, and mainly semiconductor laser chips that are based on quantum lasers. I have presented you some data that we are covering a very wide range of wavelength from red to infrared, and we have that capability in our lab, and hopefully that technology will be transferred to industry soon. One part we are going to do it in near future. Semiconductor detector chips we have made, and we have already deployed some of them in some application within the department, and especially for X-ray and gamma rays, we are now working with users. Those detectors will be optimizing, and those will be transferred to given to users. Our devices are good as compared to radiation hardness. They can take a lot of radiation load, and they won't go bad when they are exposed to radiation. And we have made some very advanced spin optoelectronic chips which can sense spin and charge simultaneously. And this work, I would like to acknowledge my team. Few of them are in audience over here. Dr. Dikshit, Dr. Khamari, Abhishek, Gitanjali, Ravi, Krishna, and Porwal. They are all of them. They have completed this lab, and especially for diode pumping, Dr. B.N. Upadhyaya and his colleagues helped us a lot. And finally, thank you all for listening to me. Thank you.
So, thank you, Dr. Kumar Sharma.
Hopefully,
we are unable to go for any question session. Hope
I was audible at the other end.
Yes, sir.
I can't hear you right now. Can you? No, actually.
Hope others can hear me now.
Sure. Yeah.
Yes, sir. You are audible.
So,
I have problem.
Thank you, Dr. Kumar Sharma, for it's an excellent talk on the fabrication of semiconductors. They covered really the front-end research work, what is going on in AutoCAD in an excellent way. Due to shortage of time, we are unable to give you more time, and we are sorry for the inconvenience from our part. So we thank exclusively for such an exclusive talk on the spin AutoCAD detectors using the front-end research work. So I thank Steve Paul of Dr. Kumar Sharma's talk today, and also Dr. Nate, Director of Arakan, for permitting Dr. Sharma to deliver this talk. Thank you all. Thank you very much. We will move to the next lecture, lecture 5. It's going to be given by monolayer molybdenum sulfide for flexible and high mobility electronics by Dr. Kishore Kumar Madapu, who is a scientific officer in Material Science section of IGCAR Kalpaka. There's a brief introduction about Dr. Madapu. He is an expert in the near field optics and near field scanning optical microscopy and spectroscopy using chip-enhanced Raman spectroscopy. He is also expertise in CPD growth of 0-dimensional, 1-dimensional, 2-dimensional semiconducting nanostructures, including monolayers of dyed organoids. Dr. Madapu obtained his MSc in physics from Uspania University, Hyderabad. He joined IGCAR Kalpaka as scientific officer in 2011. He graduated from the 5th batch of IGCAR training school. Dr. Madapu completed his PhD in 2018 from HBNI and received an outstanding doctoral student award with the Homi Bhabha Gold Medal. His thesis was started for the Best Thesis Award at the 64th DAE Science and Physics Symposium. Dr. Madapur published around 30 international journals and 2 book chapters. He attended several national and international conferences. He is a member of the India Institute of Metals and the Electron Microscope Society of India. With this introduction, may I request Dr. Kishore Kumar Madapur to deliver his talk on monolithic non-film sulfide for flexible and high mobility electronics. Over to Dr. Madapur, please.
Okay.
Yes, sir.
Thank you.
Sir,
am I audible?
Yes, sir. Yes, sir. You are audible. You can
Thank you.
share the
Yes, yes.
Sure, sure.
Yeah, this mouse is, madam, mouse is.
Two from there.
No. Nice. Sir, thank you very much for the introduction. And also,
Go ahead.
okay. So thank you very much for this opportunity, sir, actually, and also for introduction. So I'm going to talk about today the emerging semiconductor materials, such as the 2D materials, semiconductor 2D materials. Actually. This is the title of my talk. It's the monolar MOS2 for flexible and high mobility electronics. In this talk, I briefly introduce about the 2D materials, especially transition metal dichalcogenides, actually, and also how we can, as it being the monolar structures, we can exploit as the flexible electronics. However, there are some inherent limitations. So we can be one of the limitation, how we mitigated the limitation using the some novel methods, actually. And finally, we developed a miniaturized monolar structure which can enhance your absorption coefficient as well as the field effect properties, actually. So finally, I will conclude my presentation. So, you know, as you know, that 2D materials started with the discovery of graphene. So it has a very excellent properties because of their reduced dimensionality and peculiar band structures. So we know that there are the carriers behave like a Dirac fermions. But unfortunately, because of the crystal structure, we can expect a very high mobility and very excellent thermal conductivity. But unfortunately, graphene is a semi-metal, so we cannot exploit as a semiconductor applications. So the researchers started looking for the other 2D materials, so we can exploit the other 2D materials which can have a semiconducting nature. The latter, like even the silicene and germanium, also exploited, studied, and also most importantly, hexagonal boron nitride and also transitional metal halides. But most research materials are the transitional metal dichalcogenides, actually. So why they're looking for from this slide, we can say that there are plenty of 2D atomically thin 2D materials or ultra thin 2D materials which have the band gaps ranging from the metals to the insulators also. So, however, there are more studies are carried out on the two-dimensional metal transition metal dichalcogenides. These TMDs can form the 40 different 2D layer structures, actually. So from there, we can see that the band gap varying from the very 0.3 to almost to technical important band gap like a 2.1 electron volts also. So this makes the very that's why these 2D materials behave like these are the materials for the emerging semiconductor materials. So which can have the plenty of application towards the optical detectors and which can also exploit in the photovoltaics also. So one more interesting also this the 2D materials monolayer MOST is the most studied material, actually. Not only because of its monolayer, there is plenty of interesting properties. It has to it shows to the if you, when the FET device, if you make the MOS2, it has shown the on-off ratio as much as 10⁶, which is very high compared to other semiconductor devices. So not only that, it has some unique properties, especially in terms of the optical properties. When you say if the bulk MOS2 is the bulk material interdependent semiconductors, when you go to the bulk to the monolar MOS2, there is a drastic change in the your band diagram. So let's say in this particular slide, you can show that how the band diagram is changing from the bulk to the monolayer MOS2. When you go to the monolayer MOS2, there is transition from the indirect band gap to the direct band gap material. So this is one of the unique property of the monolayer MOS2, which will provide the better applications toward the optics. So this is the typical, one can visualize the how the transition happened. If you see this potential spectra, the bulk molar MOS, there is no emission in between the 1.6 to 2.1 electron volt. But if we go for the monolayer and bilayer case, we can clearly see the emission of the photoluminescence emissions. Not only that, we can see the quantum yield of photoluminescence increase more than 4 orders if you go for the bulk to the monolayer MOS2. This kind of peculiar behaviors can be exploited in many applications actually. Not only that, this also, if you see, this is the monolayer is a thickness of less than 1 nanometer. But however, it is even though it's having a 1 nanometer thickness, it can absorb almost 10% of your sunlight. So this particular application can property can be exploited in the photovoltaic effects. If you see that, if you compare this absorption coefficient with others conventional semiconductor like gallium arsenide, silicon, it is 1 order greater than the 1 order greater than absorption coefficient. So this is the area we can exploit these 2D materials for developing a optoelectronic application photovoltaic devices. More in the towards the fundamental applications and very physics point of view, these materials show the very high binding energies of excitons. As a result, if you see that the conventional semiconductors is in the 10 to 20 millielectron volts, but if you see the binding energies of these 2D materials, will have the almost 1 order higher than the conventional semiconductors. As a result, we can see that this all the photoluminescence spectroscope photoluminescence emission is dominated by the exciton emission in the room temperature. Not only that, some in the other bound particle like trions and the bi-exciton also we can able to see even in the room temperature, which is never happen, which is never seen in the case of conventional semiconductor. You know, right? These trions are nothing but the 3-particle system, either 2 electrons and 1 hole, or 2 holes or 1 electron. So in our lab, we are since 4 to 5 years onwards, we are working on these 2D materials. We established our the synthesis process such as chemical vapor deposition. Why we are choosing the chemical vapor deposition means most of the studied characterized materials are mechanically exfoliated. In case of mechanically exfoliated samples, we only make the samples not more than the 10 micrometer or 20 micrometers. But if you want the large area flakes and high growth rates, we must go to the chemical vapor depositions. So in this, our lab, we are grown the materials using the sulfur and the MO3 as the precursor materials. So where you are using the argon as the carrier gas actually. So from this slide, you can see that we have grown the regularly we are preparing and growing the material from the small flake area size to very large flake area monomer MOS2, not on the SiO2 as well as the aluminum oxide sapphire substrate. So we can we can say that we can able we can able to grow even the centimeter scale monolayer structures actually. So this is in the second row, you can clearly see that there is a large area of monolayer MOS2 which is showing the grain boundaries, which is having the centimeter scale monolayer MOS2 structure. So we have characterized these monolayer structures using the mostly in Raman spectroscopy, because it is tells about what the thickness of our grown flake actually. So from this we can see the Raman spectra showing the different for the bulk as well as the monolayer structures. From with and also we can similar to the graphene from the Raman spectroscopy can be used to estimate the number of layers in the presence in the flakes actually. So from the Raman spectroscopy we can confirm that the gold material is the monolayer structures, and also as I said, we could able to grow the MOS2 in a large area in large scale. We can also able to transfer on the the flexible electronic towards the flexible electronics. We can able to transfer on the OHV sheet. So so as it is a monolayer thickness, so we can exploit this MOS2 or other 2D materials in the flexible electronics. So for that, what we need to do, unfortunately, see, chemical vapor deposition only can give the large area flakes, but unfortunately, these CVD cannot be used to grow the material on the these flexible electronics, because flexible substrate, because they are not stable at the very high temperature, which usually the CVD deposition takes place at the 700 degrees Celsius. That's why we must transfer these monomer MOS2 from the as-grown sample to the onto the flexible substrates. So, but generally, generally, what was the problem in these flexible substrate? Transferring the ice-grown flake from the SiO2 substrate to the any other arbitrary substrates. So first we used to spin coat the PMMA over the ice-grown MOS2. Then we dip into these whole substrate with the PMMA coated capped in the KOH solution. The KOH will slowly etch out.
Hello, Kishore sir.
SiO2.
Hello, sir. You
Sorry.
stop the sharing.
One second.
Stop sharing.
Stop sharing. One second, sir. We are rectifying the problem.
Okay, sir.
We are sharing, right? Okay, sir. We are sharing once again.
Sir, your slides are visible, not okay.
Thank you. Sorry for the interruption. Now you can see, right? Yeah. This is that. This is the wet chemical etching method. We try to transfer the ice-grown sample to the other arbitrary substrate. So we are dipping the PMMA spin-coated sample on the KOH solution, where the KOH will etch out the SiO2 substrate. Then the PMMA capped MOS layer floating over the solution. So we from the solution we will fish out this PMMA capped MOS2 and clean out we will remove the stone. We will remove the PMMA using the stone cleaning. But unfortunately, this PMMA method, not only the MOS2, other graphene also used to transfer using the PMMA method. So what was the problem with PMMA polymer? There is a lot of residue polymers. These residue polymers, what will change the inherent property of the film, as even in the graphene or in case of MOS2, and also they can act as a thermal resistance to the for the heat to thermal resistance to heat. So that way, people are started looking how we can completely remove the PMMA residues. But one of the report they mentioned that we can clean the PMMA residues using the AFM in the contact mode. Unfortunately, this particular method cannot be expanded to the other large scale. Only we can in small scale only we can able to clean. But we are trying to develop a method which can be used to the completely removal of the PMMA in a bulk large scale samples. So for that we have taken the as-grown. This is the typical methods we are following. So this is the optical topographic information of the as-grown film. If you see the optical and PSM and AFM, and the next one you can see the as transfer, because transfer using the PMMA to the another SiO2 substrate, where we can clearly see from the optical as well as the SEM image there is a patches of PMMA residuals. If you go for the once again topographic small case high-resolution imaging in the AFM, we can clearly see there is a particle left over on. We can clearly see the particles left over on the MOS2. Right, these particles from the EDAX analysis we did that these particles are nothing but the PMMA chunks actually. So unfortunately, even though we are treating any waste stone for longer time, even three days also, these PMMA residues cannot be removed from the MOS2 layers. So what we studied, we are trying to understand is there any other method, and also we use the Raman potential spectroscopy for understanding the structural integrity of the transfer flake, where we found that these flakes are intact with the MOS2 structural integrity, and we tried sorry. Next, we try to remove these PMMA residues from these as transfer flakes with different methods. So first we tried with the use of ozone cleaning. So unfortunately, after ozone, if you see that this is a typical as transfer film, After ozone cleaning, we cannot able to reduce the not more than the 5 nanometer of this particular PMMA residue particle. And also we did the annealing at a moderate temperature around 200 degrees Celsius. Unfortunately, this annealing we are not removing the particles, but it is making the deteriorating the structural integrity of the MOS2. So we are also use the art stone, which is a art stone which completely modified the properties of the MOS2 with the spilling of the all particles over the substrate. So finally, we try to use the non-solvent. Stone is a solvent for the PMMA, but we are trying to use the non-solvent such as ethanol, where we tried with the ethanol treatment. See the first image of AFM image where you can, as transfer flake, where you can clearly see the particles, residue particles over the surface. But if after ethanol treatment of 24 hours, we can clearly see that there is a complete removal of the PMMA residues from the MOS2 surface. And also we have slightly increase the temperature around 30 degrees Celsius, then we can clearly see the almost residue-free monomer MOS flake from this one. So with this method, we terminalize we can able to, from this, using this novel method, we could able to produce the ultra clean monomer MOS2. This can be extended to any other 2D materials. And also this, not only the IFM analysis, we also studied the HRTM analysis for the ice transferred flake as well the ultra clean flake. We can clearly see that there is the leftover particles of PMMA, but in case of ultra clean samples, there is no leftover particles of the PMMA. And also we can clearly see there is the patches in the HRTM image with the ultra clean MOS2 does not show any patches. This confirms that our method is successfully removed the PMMA residues. So here we try to develop the what could be the mechanism for this removal of the PMMA from the using the ethanol solution, either is a non-solvent. So what we will do, we are trying to understand with the interdiffusion model. So instead of dissolving the PMMA residues, the ethanol try to penetrate between the MOS2 and the PMMA residues, it will lift over from the surface. So this is the diffusion mechanism, diffusion mechanism rather than the dissolving the PMMA particles, which is usually done by the stone. Then we have seen that as we have achieved the ultra clean monomer MOS2, but we have to see whether we can be able to improve the in electronic properties as compared to electron properties. So we made a device out of these ice prepared ice transfer MOS2 and ultra cleaned monomer MOS2 using the baguetted. In this case, we use the pre-deposited electrodes for this one. You see, this is a typical device we have made using our laser lithography. You can see that from the first row, you can show the transverse characteristic. The next one is the output characteristics. Before and the output characteristics, if you see the output characteristics, we can clearly see the perfect saturation of the current with increasing the VDS actually. So finally, what we could understand that we could be able to improve all the device parameters in case of ultra clean monomer MOS2, especially if on-off ratio also increase 1 order higher, and also the mobility also increased at almost 90 to 85% mobility, electron mobility also increasing. Yeah. So far we found that the MOS2 the high absorption coefficient. Unfortunately, with this thickness, we cannot go more than what we expected. But we would like to see if you could able to make a multi-layer structures with the intact of the monolayer behavior. So this can be possible if you make a nano scrolls out of the monolayer structures. So you can see and also we can also improve there are multiple channels for the electron transport. We can improve the electron mobility also. But so far, the literature they found that when they try to make the nano scrolls out of the monolayer, they always end up in the multi-layer behavior. So they cannot retain their monolayer structures. So what we tried actually, we have used the absolute ethanol to make a nano scrolls. As we know, we could able to generate the large scale MOS2 from the ethanol. We can see this is a photograph. The mechanism we generate how we generate the nano scrolls. So we will draft cast the ethanol solution over the large area MOS2 when it's drying. So when is the evaporating over the surface, where you can see clearly see there is a formation of the nanospore at the near the grain boundary regions. Right, then this is the typical morphological analysis by carried out using the optical microscopy as well as the EPSM and the AFM topography, where we found that the length of this nanoscale around 13 micrometer and the lateral size around the 220 nanometers. From this, we calculated the what is the number of layers present in these nanoscales around 160, 32 numbers of monomer layers. See, as I said, when scrolls are made, it should be behave like our intention to make a nanoscroll with non-interacting nature rather than the multi-layer. So how we can able to see that one? If you able to see the photoluminescence emission from these scrolls, that we can confirm that these nanoscrolls retaining their monolayer nature. See, you can clearly see that on the Raman spectroscope also, you see that the difference, as I said earlier, the difference between the two prominent Raman modes can tell the number of layers present in the flake. If you see the scroll as well as the monomer investors, both are the difference is same. That means even the scroll contains the 32 layers of MYS2, but still it is behaving like a monolayer. That means there is no interaction between the layer to layer, and also you can clearly see that there is a rise in the photoluminescence intensity, for 6 times rise in the photoluminescence intensity. That tells us we can even improve the absorption coefficient of the MYS2 by making the non-interacting monolayer nanoscrolls actually. Right, and also for the further conformity, see this non-interaction nature can come. How you can confirm from the when you have the perfect interacting flakes, we can observe always a breathing mode and the shear mode. Then we see the low frequency Raman spectroscopy. There we found that there is no shear mode as well as the breathing mode. That tells about that these nanoscrolls, the film layers present in the nanoscroll, they are not interacting together. And the Kelvin probe microscopy also tells that there is no change in the contact potential difference between the scroll region and the monomer MYS2. This confirms that these nanoscrolls are non-interacting layers actually. Right, and also we studied the photo response of these scrolls and monomer MYS2, where we found that these scrolls have shown the 6 times higher photo response compared to the monomer MYS2. This is our objective. Basically, we try to improve the properties of these monomer MYS2 by making the more number of layers with non-interaction. And also we prepared the FET devices out of these nanoscrolls, where we found that we can able to but then we compare each and every parameter from the planar MOS device and the nanoscroll MOS device, where we can find, so far we found the 2 order higher mobility. This is the first observation with no one is reported that this much mobility in case of any monolayer MOS structures. So now I conclude in the talk. Actually, we successfully prepared the one of the technological bottleneck of the residues. So we can develop with using the non-solvent of ethanol, we could able to generate the ultra clean monomer MYS2, and also we made a novel monolayer structures with multi-layers having the intact of the monolayer nature, where we found that the photoluminescence quantum yield and electronic properties are substantially improved. Thank you. Sir, sir, can we? Sir, can I stop sharing the slides actually?
Yes, sir.
Thank you. Unfortunately, we cannot hear properly.
A little volume increase so that they can hear.
Yes. That question was so well. Yes. There is other part. Because building is over and still This voice is breaking.
Sir, unfortunately, I cannot. The voice is breaking. I cannot able to hear actually.
Since September, you should get, September,
Someone cross talking.
Yeah. See, all over the some speaker get the letters. This start so that
So voice is not coming clear. Little bit louder, sir.
All over. It means for joining with this seminar on breakthroughs in research leading the India's development of Viksit Bharat. Thank you all. Thank you very much.
Thank you very much, sir. Thank you very much.